Hello there, and welcome to Physics with William, where curiosity gets cozy, the universe lowers its voice a little, and science takes the long, quiet route towards sleep. Tonight we're going to spend some time with one of the most elusive ideas in modern physics, a particle so light, so shy, and so difficult to catch that it almost feels as if nature invented it specifically to keep physicists humble. It is called the Axion, and although the name sounds a little like something you might find in a forgotten drawer of a science fiction laboratory, it may turn out to be one of the most important particles in the universe. If it exists, it could help explain why the cosmos is filled with invisible matter, why galaxies hold together, and why the laws of physics are arranged in a way that seems almost suspiciously neat. Not neat in the sense of a tidy desk, of course. Physics has never been especially good at desks, but neat in the sense that the universe appears to have avoided a strange imbalance that our best theories say should probably have been there. Before we wander any deeper into that thought, I would love to know where you are listening from tonight, and what time it is in your little corner of the world. Perhaps it is late evening where you are, and the room has gone quiet except for the soft hum of a lamp, the occasional passing car, or the gentle complaint of an old radiator doing its best. Or perhaps it is early morning, and you have found this while the rest of the day is still stretching awake. Wherever you are, you have arrived at a rather fitting subject for a peaceful science journey, because axions are all about things that are present but unseen, influential but almost impossible to touch directly. They belong to that strange category of ideas in physics that begin as a mathematical solution to one problem, then slowly grow into a possible answer to something even larger. A bit like setting out to fix a dripping tap and accidentally discovering a hidden room behind the kitchen wall. If you find this kind of slow scientific wandering soothing, or if it helps your mind settle down after a long day of clocks, messages, errands, and other small human complications, I would be very grateful if you liked the video and subscribed. It helps this quiet little corner of physics reach more people who may also enjoy drifting through the deeper questions of the universe without being shouted at by them. And as always, I do hope this is interesting enough to keep you company, but not so exciting that it keeps you awake. If it does, then at least you will have spent the evening with one of the most mysterious possible particles in nature, which is not the worst way to miss bedtime by a few minutes. The Axion is not a particle that anyone has held in a detector and proudly pointed to with a label saying, "Here it is," at least not yet. It is still hypothetical, which means it is a serious scientific possibility, not a confirmed resident of the particle family. That distinction matters. Physics is full of ideas that are beautiful, clever, and tempting, but nature is under no obligation to use any of them. Nature does not care whether our theories are elegant, whether our equations look tidy, or whether a Nobel committee has already warmed up the envelopes. It simply does what it does. The job of physics is to keep asking, measuring, doubting, and asking again until something gives. The Axion has survived that process for a surprisingly long time. It began as an answer to a problem in the physics of the strong nuclear force, and then, almost as a bonus, it became a promising candidate for dark matter. That is where the story starts to become especially interesting. Dark matter is one of the great, quiet mysteries of the cosmos. It does not shine. It does not reflect light. It does not form stars, planets, oceans, biscuits, or any of the familiar things we build our lives around. And yet, its gravitational influence appears to be everywhere. Galaxies spin as though they contain far more mass than we can see. Clusters of galaxies bend light more strongly than visible matter alone can explain. The large-scale structure of the universe, the great cosmic web of galaxies and empty spaces, seems to have formed under the guidance of something invisible. It is as if the universe were built with scaffolding that remained in place after the visible building appeared. We cannot see the scaffolding directly, but the shape of everything around it suggests that it is there. For decades, physicists have tried to work out what dark matter might be made of. It cannot simply be ordinary matter hidden in the shadows, because ordinary matter leaves traces. It interacts with light, it forms atoms, It participates in the messy chemistry of stars and gas clouds. Dark matter seems to be different. It moves through space with great calm and little fuss. It gathers under gravity but otherwise keeps to itself. This has led scientists to imagine many possible particles. Some would be heavy, some would be light, some would behave like tiny grains, others would behave more like waves spread across enormous distances. The Axion belongs to the light and subtle side of the family. If dark matter is made of axions, then the universe may be filled not with heavy invisible particles drifting like dust, but with an extremely gentle field, a quiet background presence moving through the cosmos, almost like an invisible mist. That image is useful, though of course it is only an image. An axion would not be mist in the ordinary sense. It would not be a fog you could walk through, or a cloud that would dampen your sleeve. It would be a quantum particle, or more precisely a ripple in a field, because in modern physics particles are usually understood as excitations of fields that exist throughout space. That may sound strange, but it is not too different from the idea of a wave on a pond. The pond is there, and a wave is a disturbance in it. In particle physics, the field is the underlying thing, and the particle is the ripple. The electron field gives us electrons. The photon field gives us photons, which are particles of light. If the axion field exists, then axions would be its ripples, and those ripples might be quietly filling the universe. What makes the axion especially fascinating is that it was not invented merely to solve the dark matter problem. It came from a different puzzle entirely, one buried deep inside the strong nuclear force. The strong force is the force that holds quarks together inside protons and neutrons, and holds protons and neutrons together inside atomic nuclei. It is enormously powerful over tiny distances. Without it, atoms would not exist in the way they do, stars could not shine in the way they do, and we would not be here having a calm discussion about invisible particles before sleep. The strong force is described by a theory that works extremely well, but hidden inside that theory is a possible source of imbalance. In simple terms, the equations allow the strong force to violate a certain kind of symmetry involving matter and mirror-like behavior. If that violation were present, particles such as neutrons should have a tiny but measurable internal imbalance in the way electric charge is arranged. The strange thing is that experiments have not found that imbalance. The neutron appears to be far more balanced than the theory casually permits. It is as though a recipe said that a cake may contain a handful of salt, and then every cake baked by the universe somehow contained almost none at all. You could say, well, perhaps the cook simply chose not to add salt. But if you are a physicist, that answer feels unsatisfying, because you want to know why. Why should the value be so small? Why should nature pick the quiet option when the theory allowed something much louder? This is not a problem of the theory failing in an obvious way. It is subtler than that. It's a problem of naturalness, a question about why something that could have been large appears to be extremely close to zero. Physics has a long history of treating such questions seriously, because sometimes a suspiciously small number is not a coincidence. Sometimes it is a clue. The axion was proposed as a way for nature to solve that problem dynamically. Instead of simply setting the troublesome imbalance to nearly nothing for no clear reason, the axion idea suggests that there may be a field that naturally relaxes the universe into the balanced state we observe. Imagine a marble rolling into the lowest point of a shallow bowl. You do not need to place it perfectly by hand. The shape of the bowl guides it there. In a similar spirit, the axion field would adjust itself so that the strong force ends up behaving in the balanced way experiments show. That is the original reason the axion entered physics. It was not born as a dark matter candidate. It was born as a kind of cosmic self-correction mechanism, a way for the strong force to tidy up one of its own awkward possibilities without anyone having to sweep it under the rug. Then came the extra surprise. A field like this, if it existed in the early universe, could leave behind a huge population of axions. These axions could be stable, extremely light, and very weakly interacting. In other words, They could be just the sort of thing dark matter seems to require. They would not shine. They would not collide often with ordinary matter. They would move under gravity and gather around galaxies. They might be abundant enough to account for the missing mass that shapes the cosmos. This is part of what makes the Axion so appealing. It is not a random dark matter suggestion pulled out of a hat. It solves one problem and may solve another. In physics, when a single idea opens two locked doors, people tend to pay attention. They may still keep one eyebrow raised, because that is proper scientific posture, but they pay attention. The challenge is that axions, if they exist, would be very hard to detect. They are expected to interact only faintly with ordinary matter and light. You could be surrounded by axions right now, with countless numbers passing through your body, your chair, your walls, and the planet beneath you, and you would never notice. Not because they are ghostly in a supernatural sense, but because their interactions would be so rare and so delicate that ordinary experience has no way to register them. We are used to things announcing themselves. A stone has weight. A lamp gives light. A kettle whistles, often with unnecessary confidence. But an axion would not announce itself. It would be more like a whisper in a room full of machinery, or a tiny vibration in a building during a storm. To find it, scientists have to make the room very quiet, build instruments of extraordinary sensitivity, and listen in just the right way. One of the most famous approaches to axion detection uses powerful magnetic fields. The basic idea is that, under the right conditions, an axion might convert into a photon, a particle of light. Not ordinary visible light necessarily, but a tiny electromagnetic signal that a detector could pick up. The experiment has to be tuned carefully, because the axion mass is not known. Searching for axions can therefore be a little like trying to find one specific radio station in a vast range of static, except the radio station may be extremely faint, and nobody knows exactly where on the dial it is, so researchers scan patiently. They cool equipment to very low temperatures. They shield it from noise. They improve their instruments year after year. It is slow work, but much of physics is slow work. The universe rarely hands over its secrets quickly. It prefers a long conversation. There are other ways to search too. Some experiments look for axions that might come from the sun. Others search for effects in precision measurements. Some use resonant cavities. Some use novel materials. Some use quantum sensors. And some use clever designs that sound as if they were assembled from the dreams of a very patient engineer. The details can become technical quickly, and we will come to them gently later. For now, what matters is the mood of the search. Scientists are not digging for a particle that should leave a big obvious footprint. They are listening for something that may have shaped the entire universe, while barely touching anything at all. That contrast is wonderful. The axion could be cosmically important and personally unnoticeable. It could help hold galaxies together and still pass through your bedroom without disturbing a single dust mote. This is one of the reasons dark matter is such a humbling topic. We tend to think of reality as the things we can see and touch. The table, the window, the moon, the cat who has decided that your laptop is warm and therefore legally theirs. But the visible universe may be only a small part of what is really there. Most matter, according to our best cosmological evidence, may be invisible matter of an unknown kind. That means the stars and galaxies we admire are not the whole story. They are the illuminated portions of a much larger structure. It is a little like walking through a city at night and seeing only the windows that are lit, while the buildings themselves remain mostly dark. The axion is one possible answer to what that darkness contains. Still, it is important to hold the idea carefully. The axion might not exist. Dark matter might be something else. It could be a different kind of particle, or a family of particles, or something stranger than the categories we currently use. Science does not move forward by falling in love with one explanation and refusing to look at others. It moves by testing, comparing, failing, improving, and occasionally being startled. The Axion is compelling because it is motivated by deep theory and fits many dark matter needs. But compelling is not the same as confirmed. That is part of the appeal. We are not walking through a museum of settled facts tonight. We are wandering along the edge of what is known, where the path is real but the destination is not yet visible. The name itself has a small story behind it. The particle was named after a laundry detergent brand because the idea helped clean up a problem in the strong force. Physicists, it turns out, are not immune to wordplay. You might imagine the early discussions around this idea, dense with symmetry, quantum fields and nuclear behaviour, suddenly making room for a joke about cleaning. There is something rather comforting in that. Even at the highest levels of theoretical physics, where people are trying to understand why the universe has the structure it does, someone may still pause long enough to make a pun. The cosmos may be vast and mysterious, but the humans studying it remain wonderfully human. What an axion really is, then, cannot be answered in one quick sentence, at least not honestly. It is a proposed particle. It is a ripple in a possible field. It is a solution to a symmetry puzzle in the strong nuclear force. It is a dark matter candidate. It is a target for some of the most sensitive experiments ever built. It is a bridge between the tiny world inside atomic nuclei and the enormous structure of galaxies. That range is remarkable. Few ideas connect such different scales so naturally. The axion begins in the mathematics of quarks and neutrons, then reaches outward into halos of invisible matter surrounding galaxies. It asks us to think about the smallest ingredients of matter and the largest architecture of the universe in the same breath. And this is where the story becomes a good companion for a quiet night. The axion reminds us that the universe may still contain simple things we have not yet noticed, not because they are far away, but because they are subtle. We often imagine discovery as a matter of looking farther, building larger telescopes, seeing deeper into space. And yes, that is part of it. But sometimes discovery means listening more carefully to what is already around us. It means building a detector in a quiet laboratory and waiting for a signal that may have crossed the room unnoticed since before Earth had flowers, before the sun had planets, before the first atoms settled into the first stars. If dark matter is made of axions, then they are not rare visitors. They are part of the environment of the cosmos. They are here, there, everywhere, passing through the ordinary world like a hidden layer of reality. For tonight, we can begin simply. There is a mystery in the heart of matter, and there is a mystery in the weight of galaxies. The axion sits at the meeting point of those mysteries. It was proposed because the strong force behaves more neatly than expected. It became famous because it might also supply the invisible mass that shapes the universe. And although no detector has yet confirmed it, the search has become one of the most careful and imaginative efforts in modern physics. In the slow unfolding of that search, we see something familiar about science itself. It does not always move by grand explosions of certainty. Sometimes it moves by noticing that something is a little too quiet, a little too balanced, a little too hidden, and deciding to listen more closely. So settle in a little more, let the day loosen its grip. The axion is not a loud subject, and that suits us well. It asks for patience, it asks for careful attention, it asks us to follow a thread from the dense interior of the neutron to the dark outskirts of galaxies, from the early universe to quiet laboratories filled with magnets and cooled metal chambers. We will begin with why such a particle was needed at all, because before the axion became a possible answer to dark matter, it first appeared as a solution to a very particular problem in the strong force, a problem that seemed small on paper, but pointed towards something missing in our understanding of nature. And like many good mysteries in physics, it starts not with a dramatic failure, but with a silence where there could have been noise. That silence is a good place to begin, because in physics, silence can be just as important as noise. A missing signal can be a message. A number that should be large but is not can behave like a locked door. A property that nature seems allowed to have but somehow refuses to show can make physicists uneasy in the same way you might feel uneasy if every clock in a house stopped at exactly the same minute? Perhaps it is nothing. Perhaps all the batteries failed at once. But you would still want to have a look around. The Axion entered physics because the universe appeared to be too well behaved in a particular place. Not in the familiar world of falling apples, spinning planets, or sleepy cups of tea cooling on a bedside table, but deep inside the structure of matter, where quarks, gluons, protons, and neutrons live. These are not places we can visit in any ordinary sense. No tiny ladder leads down into the middle of a neutron. There is no little door marked strong force staff only. We know this world through experiments, detectors, collisions, patterns, and the hard work of building theories that match what nature allows us to measure. And the theory of the strong force is one of the most successful pieces of modern physics. It describes how quarks are held together, how protons and neutrons exist, and why atomic nuclei can remain stable instead of immediately flying apart under the electric repulsion of positively charged protons. The strong force is, as the name suggests, strong. That may sound like physicists ran out of adjectives, which is not entirely unfair, but the name is accurate. At the tiny distances inside an atomic nucleus, it overwhelms the electric force. It binds quarks into protons and neutrons, and it helps bind those protons and neutrons into nuclei. Without it, the universe would not have atoms in the way we know them. Hydrogen might exist in a simpler form, but the rich chemistry of carbon, oxygen, nitrogen, calcium, iron, and the rest of the ingredients that make planets, oceans, bones, bread, and houseplants would not be available. The strong force is one of the reasons reality has texture. It is why matter is not just a loose scattering of lonely particles drifting through empty space with no social skills whatsoever. The modern theory of the strong force is called quantum chromodynamics, though we can simply think of it as the theory of quarks and gluons. Quarks are the small particles inside protons and neutrons. Gluons are the carriers of the strong force, and they are rather more complicated than photons, which carry the electromagnetic force. Photons do not carry electric charge themselves, but gluons carry the kind of charge that belongs to the strong force. Because of that, gluons interact with each other. This makes the strong force rich, tangled, and mathematically demanding. It is not a neat little clockwork toy. It is more like trying to describe a crowded dance floor where everyone is not only dancing with everyone else, but also changing the music as they move. Despite that complexity, the theory works very well. It explains a huge amount of particle physics. It has been tested in many ways. It is a central pillar of the Standard Model, the framework that describes the known elementary particles and forces apart from gravity. But inside this successful theory was a strange possibility. The strong force could have included a type of behavior that would slightly distinguish matter from its mirror image and from certain reversed versions of itself. In everyday terms, we are used to some things looking different in a mirror. Your left hand becomes a right hand in the reflection. A written word looks backwards. If you try to use a mirror image of a glove, you quickly discover that hands are annoyingly specific. In physics, mirror behavior matters because the laws of nature sometimes respect this kind of symmetry, and sometimes they do not. One of the great surprises of 20th century physics was that some forces do not treat mirror images in exactly the same way. The weak nuclear force, which is involved in certain kinds of radioactive decay, famously violates mirror symmetry. It has a preference. It behaves in a way that tells left from right at the deepest level. This was shocking when it was discovered, because many people assumed nature would be more symmetrical. But nature does not always share our taste for balance. The weak force also violates a related combination of symmetries involving charge and mirror reflection. That matters because these symmetry violations help us understand why the universe can contain more matter than antimatter, though that is another long walk through another quiet forest of physics. The strong force, however, seems not to show this particular kind of violation, at least not in any detectable way. The theory says it could. Experiments say that if it does, the amount must be extraordinarily tiny. This is where the discomfort begins. It is not simply that a measurement came out small. Small things happen all the time. Dust motes are small. Neutrino masses are small. The amount of patience left in a person after assembling flat-pack furniture can be very small indeed. The problem is that the strong force had no obvious reason to choose such an extremely tiny value. It looked as though nature had set a dial almost exactly to 0, even though the theory did not explain why the dial should be there. Physicists do not like unexplained dials. They tolerate them when they must, but they rarely feel peaceful about them. If a theory contains a value that can be anything, and experiments show it is almost exactly one particular value, a question appears. Why that value? Why not another? Sometimes the answer is just that nature chose it, and we have to accept that. But often, in the history of physics, a strange value has pointed toward a missing idea. The motion of planets pointed toward gravity. The orbit of Mercury pointed toward relativity. Patterns in atomic spectra pointed toward quantum mechanics. Missing energy in certain decays pointed toward the neutrino. A gap in understanding can be the outline of something real, like the shape left in the dust when a book has been moved from a shelf. In this case, the missing explanation concerned why the strong force appears to preserve a certain balance so precisely. The most direct experimental place to look is the neutron. A neutron has no overall electric charge, which is why its name is so pleasingly sensible, but it is not an empty neutral ball. It is made of charged quarks moving and interacting inside it. If the strong force violated the relevant symmetry in the way the theory allowed, the neutron would be expected to have a tiny separation of electric charge inside it. One side would be ever so slightly more positive, the other ever so slightly more negative. This is called an electric dipole moment. You do not need the technical details to feel the idea. Imagine something that is neutral overall, but has a subtle internal direction, like a tiny compass needle made not of magnetism but of charge. Experiments have searched for this neutron imbalance with great care. They have not found it. That means the imbalance, if it exists at all, is far smaller than the theory might naturally suggest. This is not a small inconvenience. It is a deep puzzle about why one of the main forces of nature behaves as though it has been carefully tuned. The universe seems to have avoided a feature that would have been allowed. It is like discovering that a noisy old machine has a volume knob, and for some unexplained reason it has always been set almost perfectly to silence. You can shrug and say perhaps that is just where the knob is. Or you can ask whether there is some hidden mechanism constantly turning it down. The Axion was born from the second attitude. It came from the idea that the silence was not an accident, but the result of a process. Instead of assuming that the strong force simply began with the troublesome setting already near 0, physicists Roberto Peccei and Helen Quinn proposed a new kind of symmetry that would make the setting adjust itself naturally. A new field would exist throughout space, and the behaviour of that field would drive the strong force toward the balanced state we observe. The particle associated with that field was later called the Axion, so the Axion was not introduced as decoration. It was not a spare particle added because the standard model looked a little lonely on a shelf. It was introduced because it gave the universe a way to explain its own restraint. This is an important point. The universe did not need an Axion in the emotional sense, of course. The universe is not sitting somewhere feeling that its particle collection lacks completion. When physicists say the universe needed something, they usually mean that our description of the universe seemed to contain a problem that could be naturally resolved if that thing existed. The Axion made the strange quietness of the strong force less mysterious. It turned a fixed, unexplained number into the result of a field settling into place. The difference is subtle but powerful. A fixed, unexplained number feels like someone has typed in an answer without showing the work. A field that relaxes into the right value feels like a physical reason. A simple analogy may help. Imagine a round table in a room, and on the table there is a marble. If someone tells you that the marble is sitting exactly at one particular point on the surface, you might ask why. Perhaps someone placed it there. Perhaps it is glued down. Perhaps it is coincidence. But if the table is actually shaped like a bowl, the answer becomes easier. The marble rolls to the lowest point because the shape of the table guides it there. You do not need to fine-tune the starting position. The system naturally finds the stable place. The Axion idea works with a similar spirit. The field associated with the Axion changes the situation so that the balanced behaviour of the strong force is not an arbitrary choice. It is the natural resting point. This kind of thinking appears often in physics. When a system has a stable state, it tends to move toward it. A pendulum settles downward. A ball rolls into a valley. A hot drink cools toward the temperature of the room, although never as slowly as one would like when one is impatient for tea. The Axion field would have its own preferred state, and when it settled there, the strong force would lose the unwanted imbalance. This is elegant because it explains why the measured effect is so tiny, without requiring an improbable initial setting. It also gives scientists something to look for. If there is a field, there should be a particle. In quantum field theory, fields and particles are connected. The field is the underlying presence. The particle is a ripple of that presence. The axion is the ripple. At first, the axion seemed as though it might be relatively easy to find, at least by the standards of particle physics, where easy can still mean building a machine the size of a small town and waiting years for a bump in a graph. Early versions of the Axion idea suggested a particle with properties that experiments could test. Those early versions were soon ruled out. The Axion, if it existed, could not have the original simple form, but the idea did not die. It changed. More subtle versions appeared, with axions that were lighter, weaker, and far more difficult to detect. Instead of being a particle that would show up readily in ordinary accelerator experiments, the axion became something quieter. It became a particle that could hide almost perfectly. That might sound like moving the goalposts, and physicists are rightly suspicious of theories that survive every failed test by becoming harder to test. But in this case, the more elusive axion was not just an excuse. It came from broader versions of the original mechanism that still solved the strong force problem. These versions predicted axions with very weak interactions and very small masses, and then something remarkable happened. Those very properties made the axion a possible dark matter particle. The same features that made it hard to find also made it cosmologically interesting. It would be stable, it would not shine, it would not interact much with ordinary matter. It could have been produced in large quantities in the early universe. It could still be here now, spread through galaxies as a vast invisible population. This is the moment when the Axion story grows from a nuclear puzzle into a cosmic one. The particle was originally invited in to solve a problem inside the strong force, but it arrived carrying a second possibility. It might help explain the missing matter of the universe. That is a rare and attractive feature. Many proposed particles solve one theoretical issue but create no clear connection to observation. Others are invented mainly to explain an observation, but have no deeper theoretical motivation. The Axion has both. It is motivated from within particle physics, and it may answer a major question in cosmology. That does not prove it is real, but it makes the idea unusually compelling. It is as though one key might fit two doors in completely different parts of the house. To see why that matters, it helps to remember how large the dark matter problem is. Galaxies do not rotate the way they would if the only matter in them were the stars, gas, and dust we can see. The outer regions of galaxies move too quickly. Galaxy clusters hold together too strongly. Light from distant objects bends too much as it passes near massive structures. The cosmic microwave background, the afterglow of the early universe, carries patterns that make the most sense if dark matter was present from very early times. The universe, on its largest scales, appears to have been shaped by something invisible. Ordinary matter fell into gravitational wells created by this dark component, forming galaxies and clusters along a hidden framework. If dark matter were removed from the story, the universe would not grow into the one we observe. So physicists needed dark matter, and they needed it to have certain properties. It had to gravitate. It had to be long-lived. It had to avoid interacting strongly with light, otherwise we would see it. It had to avoid interacting too strongly with ordinary matter, otherwise it would already have shown up clearly in experiments or changed the behaviour of stars and galaxies in ways we do not observe. It also had to be produced in the right amount. This is not a small shopping list. It is more like trying to order a perfectly specific part for a very old machine from a catalogue written in a language nobody fully speaks. Heavy dark matter candidates were studied for decades and remain possible, but the Axion offered a different route. It suggested that dark matter might be extremely light, not heavy, and that its abundance might come from the early behaviour of a field rather than from ordinary particle creation in a hot cosmic soup. That field-based origin gives Axion dark matter a different character. If axions are the dark matter, then in many scenarios they behave less like a swarm of individual pellets and more like a coherent wave spread across large regions. This does not mean they are not particles. In quantum physics, the line between particle and wave is not a wall. It is more like a change in how we choose to describe behaviour. A large population of very light axions could act like a field oscillating gently through space. The word oscillating here simply means changing back and forth in a regular way, like a pendulum or a vibrating string, though the axion field would be far more subtle than either. Detectors searching for axions often try to find the tiny effects of that field as Earth moves through the dark matter halo of our galaxy. There is something quietly strange about that possibility. The room around you may contain not just air, warmth, light, and the usual collection of ordinary matter, but also a dark matter field passing through everything. It would not brush your skin. It would not rustle curtains. It would not make a sound. And yet, if axions make up dark matter, that field would help explain why the Milky Way holds together. It would be part of the gravitational environment through which the Sun, the Earth, and all of us move. We often imagine dark matter as something distant, out there in the black spaces between stars. But if it exists as expected, it is here too. It passes through the laboratory, the mountain, the ocean, the sleeping city, and the cup on the bedside table. The difficulty is not that dark matter is far away. The difficulty is that it barely speaks to the matter we're made of. The Axion also appealed to physicists because it was not too disruptive. A good new particle must do enough to solve the problem, but not so much that it ruins everything else that already works. This is a delicate requirement. The standard model has passed many experimental tests. You cannot simply add a new particle with strong obvious effects and expect nobody to notice. It would alter particle decays, stellar behaviour, laboratory measurements, and cosmological history. The Axion is subtle enough to slip through these constraints if its properties fall in the right range. That makes the search both exciting and frustrating. A louder Axion would already have been found or ruled out. A quieter Axion can remain possible, but finding it requires extraordinary care. The universe needed an Axion then, only in the sense that the Axion gave physicists a natural explanation for something otherwise puzzling. It took a strange absence in the strong force and turned it into the expected result of a hidden field. Then it offered a serious dark matter candidate almost as an added gift. No wonder the idea stayed alive. It connected the neatness of the neutron to the weight of galaxies. It linked a tiny unmeasured electrical imbalance to the invisible structure of the cosmos. That is the sort of connection physics is always hoping to find. Not because nature must be simple, but because sometimes the same underlying principle appears in places that once seemed unrelated. And yet, there is a caution tucked inside all this. A beautiful explanation is still only an explanation until nature confirms it. The Axion may be the answer. It may be one part of a larger answer. It may be a brilliant idea that turns out not to be realized in our universe. Physics has known all three outcomes before. The important thing is that the Axion makes predictions, however difficult they are to test. It suggests interactions with light in magnetic fields. It suggests possible signals from the sun. It suggests effects in carefully designed laboratory instruments. It suggests a dark matter field with properties that experiments can search for step by step. That is why the Axion is not merely a philosophical preference for tidiness. It is a testable proposal, even if the test requires patience, cold equipment, strong magnets, and a willingness to listen for a whisper that may take decades to hear. The deeper we look at this story, the more the phrase "why the universe needed an Axion" begins to mean something very specific. It needed a way to explain why the strong force does not seem to violate a symmetry it could have violated. It needed a way to avoid fine-tuning, or at least to replace it with a physical process. It needed a candidate for the missing matter that shapes galaxies without shining. The Axion sits precisely at that intersection. It is not a random invention. It is a response to pressure from theory and observation at the same time. A pressure that says something is missing, something quiet, something that may connect the smallest and largest scales we can study. There is a pleasant humility in this. Human beings notice stars turning too fast, galaxies bending light too strongly, and neutrons behaving too evenly. From these clues, separated by enormous differences in scale, they imagined a particle so faint that it could pass through nearly everything and still matter to the whole universe. That is the kind of thinking physics often asks of us. To take tiny deviations seriously. To treat absence as evidence, but only carefully. To build a bridge from the invisible to the measurable. To admit that the visible world may depend on something hidden in plain sight. The next step is to move closer to the original puzzle itself, because the Axion cannot really be understood without understanding the strong force problem that first brought it into the conversation. We have circled it gently, like approaching a sleeping cat you do not wish to startle. Now we can look more directly at what made that problem so strange. It involves symmetry, matter and mirror images, the neutron, and a question that sounds almost too small to reshape particle physics. Why does the strong force stay so quiet when the theory says it could have spoken much louder? We left the story with a question that sounds small enough to misplace under a stack of laboratory notes. Why does the strong nuclear force stay so quiet when our theory says it could have spoken much louder? That question is the strong charge and parity mystery, often shortened by physicists into a compact name that hides just how strange the problem really is. It is not a mystery about why the strong force exists, or why protons and neutrons hold together, or why atoms can build the familiar furniture of the world. Those are deep questions too, of course, but this one is more specific. It asks why the strong force seems to obey a certain balance with extraordinary precision, even though the mathematics that describes it allows that balance to be broken. To understand why this is troubling, we need to spend a little time with the idea of symmetry. In ordinary life, symmetry is easy to picture. A butterfly looks roughly the same on the left and right. A snowflake has repeating patterns. A calm lake can reflect trees so neatly that the world seems to have folded itself in half. In physics, symmetry has a broader meaning. It means that you can change your point of view or transform a system in some specific way, and the underlying laws still behave the same. If you do an experiment today and then do it tomorrow under the same conditions, you expect the same result. That expectation is connected to a symmetry in time. If you rotate a perfectly controlled experiment in space, you expect the laws of physics not to suddenly change their mind because the apparatus is facing east instead of west. That is connected to a symmetry of direction. Symmetries are not just pretty, they are useful. They tell physicists what can happen, what cannot happen, and which quantity should be conserved. The two ideas involved here are charge and parity. Charge, in this context, is connected to swapping particles with their antimatter counterparts. A particle and its antiparticle can have opposite electric charges, and in many cases they behave like mirrored partners in the deeper bookkeeping of nature. Parity is connected to mirror reflection. It asks what happens if the universe is viewed as though left and right have been swapped. Imagine filming a physics experiment and then watching it in a mirror. Would the mirrored version still be a possible experiment under the same laws of nature? For a long time, many physicists assumed the answer would be yes. It seemed natural that the universe would not care about left and right in any deep way. After all, a ball falling under gravity does not seem to fall differently just because you look at it in a mirror. Then the weak nuclear force surprised everyone. The weak force, which is involved in certain radioactive decays and in the processes that allow stars to shine, does care about left and right. It violates mirror symmetry. It behaves in a way that distinguishes one-handedness from the other. This was one of the great shocks of modern physics, because it showed that nature is not always as balanced as human intuition expects. Later, physicists also learned that the weak force can violate the combined symmetry of swapping matter with antimatter and reflecting left with right. This matters because it gives the laws of physics a way to treat matter and antimatter slightly differently. Without some difference like that, it would be hard to understand why the universe today contains so much matter and so little antimatter. So symmetry breaking is not automatically bad. In fact, it is essential. The universe we observe depends on certain symmetries being broken in certain ways. The problem with the strong force is not that symmetry breaking would be impossible. The problem is that the strong force appears to avoid a kind of symmetry breaking that it seems allowed to have. The theory of the strong force contains room for a particular imbalance involving charge and parity. If that imbalance were present, it would show up in measurable ways. The most famous place to look is the neutron. A neutron is electrically neutral overall, but it is not simple. It is made of quarks, and those quarks carry electric charge. The inside of a neutron is a storm of strong force activity, with quarks and gluons constantly interacting. If the strong force violated charge and parity symmetry in the allowed way, the neutron should behave as if it has a tiny internal separation of electric charge. It would still be neutral in total, but one side would be very slightly different from the other. This kind of internal charge separation is called an electric dipole moment. You can think of it as a tiny arrow hidden inside the neutron, a preferred direction in how its charge is arranged. Experiments have searched for that tiny arrow again and again. The result has been silence. Not a vague silence, not a silence caused by careless instruments, but a carefully measured silence. The neutron, as far as experiments can tell, does not show the expected internal imbalance. If it has an electric dipole moment at all, it is fantastically small. The limit is so severe that the troublesome setting in the strong force must be less than about 1 part in 10 billion. In everyday terms, that is like saying a dial that could point anywhere around a full circle is found so close to one special position that you would need a microscope for the microscope just to notice the difference. That is what makes the problem unsettling. The theory does not clearly demand that the setting be so tiny. It simply permits it. Nature then appears to choose a value almost exactly equal to nothing. Sometimes this happens in science, and we accept it because there is no deeper explanation. But physicists have learned to be cautious around such coincidences. When something that could naturally be large is found to be incredibly small, it often suggests that a hidden mechanism is at work. The smallness may not be an accident. It may be protected by a principle we have not yet identified. There is another layer that makes the issue even more awkward. The strong force is not sitting alone in the universe like a hermit in a cottage. It is part of the broader standard model, alongside the weak force, electromagnetism, and the known matter particles. The weak force does violate the combined charge and mirror symmetry. The quarks also have properties that can feed into the same overall question. In the full theory, the relevant setting for strong force symmetry is not simply one clean number that we can casually choose and forget. It is affected by the structure of the quark sector as well. The strange part is that all contributions still combine in such a way that the final result must be extraordinarily close to zero. It is as if several musicians were playing different notes, and somehow the total sound cancels into near-perfect silence without any conductor visibly guiding them. This is why just saying maybe the number is 0 feels unsatisfying. It might be true as a statement, but it does not explain why. Physics can live with unexplained facts, but it does not stop being curious about them. If the strong force setting is nearly 0 simply because nature chose it that way, then we have to accept a remarkable coincidence. If, however, there is a new symmetry or a new field that forces the setting towards 0, then the silence becomes understandable. The axion belongs to that second possibility. Before bringing the axion back in, it is worth sitting for a moment with the size of the issue. This is not a practical problem in the ordinary sense. It does not prevent engineers from building bridges, doctors from reading scans, or satellites from guiding your phone through an unfamiliar city. The strong force works. The standard model works. The neutron is measured. The experiments are careful. The issue is conceptual. It is a question about why the laws have the shape they do. Those questions can seem remote, especially when compared with everyday concerns like getting enough sleep or remembering whether you left the oven on. But conceptual problems have a way of reshaping science. They're often where new physics first appears, not as a dramatic explosion, but as a small inconsistency in the pattern. Think of the strong charge and parity mystery as a tiny crack in a very well-built wall. The wall is not falling down. It shelters a great deal of successful physics. But the crack is there, and if you follow it carefully, it may lead to a hidden room. The axion is the proposed room behind the crack. It says that the strong force is quiet because the universe contains an additional mechanism that makes it quiet. More specifically, the idea introduces a new symmetry, now called the Pesay-Quinn symmetry, after the physicists who proposed it. When that symmetry is included, the troublesome strong force setting is no longer just a fixed number. It becomes connected to a field. That field can adjust, it can settle, it can roll into the state where the unwanted charge and parity violation disappears. This is an important shift. Without the axion idea, the strong force problem looks like a dial that was mysteriously set to almost 0 at the beginning. With the axion idea, the dial becomes attached to a physical system that naturally turns itself towards 0. You no longer need to explain why someone set it so carefully. The system does the work. The balanced state is not an arbitrary coincidence. It is the place where the field comes to rest. The particle associated with this new field is the axion. In modern physics, fields are not optional background decorations. They are the basic ingredients from which particles arise. An electron is understood as an excitation of the electron field. A photon is an excitation of the electromagnetic field. If the axion field exists, then axions are its excitations. That means the axion is not just a name pasted onto a mathematical fix. It would be a real physical particle, although an extremely elusive one. Its existence would tell us that the strong force mystery was not solved by chance, but by a hidden layer of reality. The consequences are enormous because this tiny strong force puzzle points beyond the known particle family. The standard model is already full of particles, but it has no confirmed axion. Adding one means adding a new field that stretches through space. It means the universe has a new kind of subtle structure. It means a problem inside the neutron may be connected to something that fills galaxies. That is a remarkable jump in scale. We begin with a measurement so delicate that it concerns the internal charge arrangement of a particle smaller than an atom, and we may end with the matter that shapes the rotation of galaxies. There is also a deeper lesson about how physics works. A problem does not need to be large in everyday units to be large in meaning. The missing electric dipole moment of the neutron is tiny. The strong force setting must be tiny. The axion, if it exists, may have a tiny mass and incredibly weak interactions. And yet the idea can carry enormous weight. It can explain why a fundamental force behaves as it does. It can provide a dark matter candidate. It can motivate experiments across the world. each trying to catch the faintest possible signal from a particle that may barely interact at all. The scale of a clue is not the same as the scale of the truth it may reveal. The strong charge and parity mystery also helps explain why physicists did not simply invent the axion for dark matter and then go hunting. The axion has a pedigree. It comes from a specific theoretical need. Long before it became one of the most discussed dark matter candidates, it was a solution to this symmetry problem. That matters because dark matter candidates are plentiful. Theoretical physics has no shortage of possible invisible particles. Some are heavy, some are light, some are part of a larger speculative frameworks, and some have names that sound as though they were invented by a committee, trapped in a basement with too much coffee. The axion stands out because it was required by a separate problem. It did not begin as an answer to the missing mass of the cosmos, it became one. There is a pleasing restraint in the original idea. It does not say that the strong force problem is solved by forcing the universe into an arbitrary value. It says the universe has a reason to choose the value. A symmetry is introduced. The symmetry is broken in such a way that a new field appears. That field relaxes the problematic setting toward the observed quiet state. The axion is left behind as the particle associated with that process. This is the kind of mechanism physicists often find satisfying, because it replaces coincidence with dynamics. Things happen because something moves, settles, or responds, not because a number was simply placed by hand. Of course, satisfying does not mean true. Nature is not obliged to reward elegance. The axion could be absent. The strong charge and parity mystery could have another solution. Perhaps there is some deeper principle that sets the value exactly to zero. Perhaps the structure of quark masses or high-energy physics beyond our current reach explains the cancellation. Perhaps the problem is telling us something even stranger. But the axion remains one of the cleanest and most compelling possibilities because it does several jobs at once without immediately contradicting what we already know. The experimental side of the story is equally patient. Searches for the neutron-electric dipole moment continue to improve. Each new limit tightens the mystery. If an experiment eventually found a non-zero result, it would be a major discovery, a sign of new physics and a clue about how symmetries are broken. If experiments keep finding nothing, the need for an explanation remains. At the same time, axion searches continue in laboratories, designed to detect faint conversions between axions and light, or tiny shifts caused by axion fields. The strong force mystery and the dark matter search therefore lean toward each other. One comes from precision particle physics, the other comes from astronomy and cosmology. Together they form a kind of quiet pressure on our understanding. It is worth noticing how unusual this is. Many people imagine particle physics as a field driven mainly by smashing particles together at higher and higher energies. That is certainly one path, and it has revealed astonishing things. But the axion story shows another path. Sometimes we look for new physics not by making louder collisions, but by making more sensitive measurements. We measure the neutron more carefully. We listen for tiny electromagnetic signals in powerful magnets. We cool instruments until thermal noise quiets down. We isolate equipment from vibrations, stray fields, and everyday interference. The search becomes almost monastic. Instead of shouting into the universe, we sit very still and ask whether the universe is whispering. The strong charge and parity mystery is therefore not just a technical puzzle. It is a reminder that the known laws of physics still contain unanswered why questions. The standard model tells us a great deal about what particles do. It does not always tell us why its own settings are what they are. Why do the particle masses have their values? Why are there 3 families of matter? Why is there more matter than antimatter? Why is the strong force so perfectly quiet in this one symmetry channel? The axion is one proposed answer to one of those questions, but it opens onto many others. If the axion exists, then the neutron has been quietly pointing toward dark matter for decades. Every failed attempt to find its electric dipole moment would not be a dead end, but a sign that the axion field is doing its job. The The absence would become evidence of a hidden presence. That is one of the most elegant reversals in science. Nothing appears, and that nothing suggests something. Silence becomes the shape of a particle. This is also why the Axion feels different from an ordinary missing object. It is not like losing a key and deciding it must be under the sofa. It is more like hearing an orchestra stop at exactly the right moment, again and again, and inferring that there must be a conductor you cannot see. The strong force does not display the charge and parity violation it could have displayed. The neutron does not show the internal charge error it could have shown. The measurements keep saying no, and the no is so precise that it becomes meaningful. The Axion is the possible explanation for that meaningful no. As we continue, the focus naturally shifts from why the Axion was proposed to what would have happened if such a field existed in the young universe. Because the same field that could have settled the strong force into balance would not simply vanish from the story. It would have had a history. It would have been present when the universe was hot, dense, and rapidly changing. It might have begun displaced from its resting state. It might have started moving as the cosmos cooled. And in that motion, in that early settling, it could have produced a vast population of axions that remained until today, quietly filling the dark halos around galaxies and passing unnoticed through the ordinary world. To picture the birth of axions, we have to let the universe become very young again. Not young in the way a planet is young, still hot and restless beneath a thin crust. Not young in the way a star is young, still gathering itself from gas and gravity. We have to go much farther back than that, to a time before planets, before stars, before atoms, before even protons and neutrons had settled into the familiar particles that later became the ordinary matter of the world. The early universe was not a place with objects sitting inside it like furniture in a room. It was the room, the furniture, the heat, the light, and the rules of motion all tangled together in an unimaginably dense and energetic state. In that first great beginning, the universe was extremely hot. Particles did not yet have the calm lives we associate with matter today. They appeared, disappeared, scattered, transformed, and exchanged energy in a restless sea. The fields of nature filled space, but they didn't always behave as they do now. Some symmetries that are hidden today may have been obvious then. Some particles that are heavy and rare now may have been common. The young universe was like a kitchen in the middle of a very enthusiastic meal, with every pot boiling, every surface covered, and nobody yet certain where the teaspoons had gone. Out of that heat and motion, the later order of the cosmos slowly emerged. The Axion, if it exists, belongs to this early story because it would not simply appear one day in an empty universe. It would be connected to a field present throughout space, and that field would have had a history. This is one of the most important things to remember. When physicists talk about axions being born in the early universe, they are not usually imagining a little factory producing individual particles one by one, each with a tiny stamp reading approved for dark matter. They are thinking about the behavior of a field as the universe cooled. A field can store energy. It can be displaced from its resting state. It can begin to move, and when it moves in the right way, that energy can behave like a population of particles. The Axion field was introduced to solve the strong force symmetry problem. It gives the universe a way to settle the strong nuclear force into the quiet, balanced state we observe. But in the earliest moments, before that settling was complete, the Axion field might not have been sitting calmly at the bottom of its preferred state. It may have been pushed away, or chosen a value more or less randomly in different regions, depending on exactly when certain events took place in cosmic history. As the universe expanded and cooled, conditions changed. The strong force itself changed character, as quarks and gluons became confined inside protons, neutrons, and other composite particles. Around that transition, the Axion field would begin to feel the shape of its resting place more strongly. A useful image is a marble on a very shallow surface. At first, when the universe is extremely hot, the surface may be almost flat. The marble has no clear direction in which to roll. It can sit almost anywhere. Then, as the universe cools, the surface slowly develops a slope and a valley. The marble suddenly has a preferred direction. It begins to move toward the lowest point, but it does not simply glide down and stop instantly. It rolls, overshoots, comes back, and continues moving back and forth around the bottom until its motion is damped by the expansion of the universe. The Axion field would do something broadly similar. As the early universe cooled, the field would begin to move toward the state that solves the strong force problem. That motion, spread across space, could leave behind Axion dark matter. This process is often described as a kind of misalignment. The word is plain and helpful. The Axion field starts out not quite aligned with its final resting state. It is not where it will eventually want to be. Later, when the cosmic conditions change, the field begins to correct itself. The energy stored in that correction does not disappear. It becomes the energy of axions. These axions would be extremely cold in the cosmological sense, meaning they would move slowly compared with light, and would behave in a way that allows gravity to gather them into large structures. That is exactly the kind of behavior dark matter needs. It must not rush around too quickly, or it would smear out the growing structure of the universe. It must be able to clump gravitationally, forming halos around galaxies and helping ordinary matter collect into stars and gas clouds. This is quite different from the way many familiar particles are produced. In the hot early universe, ordinary particles were often made through collisions. Energy became matter, matter became energy, and the cosmic soup maintained a kind of thermal balance. As the universe cooled, some particles stopped being produced efficiently, and their numbers froze into place. That is one common way to imagine relic particles surviving from the early universe. But axions can be produced in another way, from the coherent motion of a field. The field itself stores energy across large regions of space, and as it begins to oscillate gently around its resting state, that energy behaves like a sea of axions. It is not a violent birth. It is more like the universe exhaling a long, quiet note. There are several possible versions of this story, and which one is correct depends on details we do not yet know. One key uncertainty is when the symmetry associated with the Axion field became important relative to cosmic inflation. Inflation is the idea that the very early universe may have expanded extremely rapidly for a brief period. If inflation happened after the Axion field had already chosen a value, then the region that became our observable universe could have been stretched from a tiny patch with nearly the same initial Axion field value everywhere. In that case, the Axion dark matter abundance depends strongly on that initial value. The universe we can see would have inherited one common starting point for the field. If the Axion-related symmetry became important after inflation, the situation is different. Then different regions of the universe could choose different starting values for the Axion field. The cosmos would become a patchwork of regions where the field points in different directions in its internal space. As the universe cools, these regions would evolve, and boundaries or defects could form between them. These defects might later decay, producing additional axions. That makes the total axion abundance harder to calculate, but also rich with possible consequences. In one version, axions are born mainly from the smooth settling of the field. In another, they're also produced by the decay of cosmic strings and other structures left behind by the early field. These are not strings like tiny bits of thread floating through space. They are field configurations, stretched regions where the field is arranged in a special way. Still, the image of the young universe woven with hidden strands is not too misleading, as long as we remember it is a physical field doing the weaving, not cotton. The details of these early processes matter because they help determine the possible mass of the axion and how much dark matter it could make. If axions are too abundant, the universe would contain too much dark matter compared with what we observe. If they are too rare, they could still exist but would not explain all of the missing mass. This is one reason Axion physics connects theory, cosmology, and experiment so closely. The properties needed to solve the strong force problem influence how axions interact. The way the field evolves in the early universe influences how many axions survive. The amount of dark matter we measure in galaxies and the cosmic microwave background then tells us which possibilities remain plausible. A particle proposed to explain a symmetry puzzle becomes tied to the entire thermal and expansion history of the cosmos. It is worth slowing down here because the phrase field oscillation can sound mechanical, as though space contains a tiny pendulum swinging somewhere behind the curtains. The reality is subtler. A field has a value at each point in space. When the field is displaced from its lowest energy value, it can change over time. If the conditions are right, that change becomes regular. In quantum language, the energy in that regular field motion corresponds to particles. For Axion dark matter, the number of particles could be enormous, because each axion would be extremely light. A large amount of total dark matter mass could be made from an almost unimaginably large number of tiny axions moving together in a coherent way. This is why Axion dark matter is sometimes described more like a wave than like a collection of separate little marbles. That wave-like character gives axions a special kind of gentleness. Heavy dark matter particles, if they exist, would behave more like individual particles passing through detectors occasionally. Axions, depending on their mass, may behave like a background field that changes in time as Earth moves through it. Detecting them can therefore mean looking not for a single collision, but for a tiny repeating effect. This is one reason many Axion experiments use resonant devices. They try to tune an instrument so that it can respond to the faint frequency associated with the Axion field. Again, no equations are needed to grasp the feeling of this. Imagine a room so quiet that you can hear a distant note only when the instrument in your hands is tuned to the same pitch. If it is tuned wrongly, the note passes unnoticed. If it is tuned correctly, the instrument begins to respond. In the early universe, however, the Axion field was not a laboratory signal. It was part of the whole cosmic environment. As space expanded, the density of radiation fell. The temperature dropped. Particles that once moved freely became locked into new forms. The strong force grew confining, pulling quarks into bound states. The Axion field, sensitive to the strong force, began its settling motion. This would have happened long before atoms formed, long before light could travel freely through the universe, long before the first stars. By the time the cosmos became transparent and released the ancient light, we now observe as the cosmic microwave background, axions, if they were dark matter, would already have been present as a quiet gravitational component. They would not glow in that ancient light, but they would influence the pattern of matter and radiation through gravity. This is part of what makes dark matter from axions so attractive. It can be present early enough to help structure form. Ordinary matter in the young universe was tightly coupled to light for a long time. Radiation pressure kept it from collapsing too quickly. Dark matter, because it does not interact with light in the same way, could start gathering gravitationally earlier. It created the gravitational wells into which ordinary matter later fell. If axions made up that dark matter, then the gentle settling of a field tied to the strong force would have helped lay down the invisible scaffolding of galaxies. The same field that solved a tiny symmetry puzzle inside particle physics could have shaped the future homes of stars. There is something almost modest about that role. Axions would not make bright fireworks in the sky. They would not form glowing clouds. They would not gather into ordinary lumps you could stand on. They would simply provide gravity, patiently and invisibly. Their presence would be known through motion. Stars orbiting in galaxies, galaxies moving in clusters, light bending around massive structures, tiny temperature patterns in the early universe. The axion itself would remain hidden, but its collective weight would guide everything visible. It is a bit like the bass line in a quiet piece of music. You may not always notice it directly, but the whole structure changes if it is removed. The birth of axions also reminds us that the early universe was not merely a hot explosion of particles. It was a place where fields changed their identities, symmetries broke, and hidden structures formed. Many of the features we take for granted today may be leftovers from those transitions. The fact that matter has mass is tied to a field settling into a particular state. The fact that the strong force confines quarks is tied to how that force behaves at low energies. The possible existence of axions would add another layer. It would mean that dark matter is not just an unknown substance added to the cosmic inventory, but a relic of a field that once adjusted the laws of the strong force into their observed form. There is also a gentle caution here. The exact birth story of axions is not settled because the particle has not been discovered. Physicists can calculate possibilities, simulate early universe scenarios, and compare them with observations, but without knowing the axion mass and its interactions, the story remains a set of plausible paths rather than a single confirmed route. Some axions could be produced by field misalignment, some could come from cosmic defects, some could be emitted from hot plasmas, though those may behave differently and might not form the cold dark matter we are looking for. There may even be a broader family of axion-like particles, cousins of the original axion, with similar behaviour, but not necessarily tied to the strong force problem. These possibilities widen the search. They also make the word axion a little richer than it first appears. The original axion has a specific job. It solves the strong charge and parity mystery. Axion-like particles are broader possibilities that appear in many theories beyond the standard model, especially in ideas that involve extra fields or deeper symmetries. Some of them might be dark matter, some might not. Some might be detectable through their interactions with light. Some might be so faint that even our best instruments would struggle for a very long time. For this story, though, the most compelling version remains the one where the axion is both the cleaner of the strong force problem and the hidden matter of the cosmos. That double role gives it a special place. If we follow the field through cosmic time, the picture becomes almost chronological. At first, the universe is hot and dense, and the axion field has not yet settled into its final role. Then a symmetry breaks, giving the field its character. Depending on whether this happens before or after inflation, the observable universe either inherits one smooth starting value or becomes a patchwork of different regions. Later, as the strong force changes with cooling, the axion field begins to feel its preferred resting point. It starts to move. Its energy becomes stored as cold axions. The universe continues expanding. Radiation thins. Ordinary matter eventually forms atoms. Gravity amplifies tiny density differences. Dark matter gathers first, ordinary matter follows, and galaxies begin their long growth. Through all of this, the axions remain quiet. They do not decay quickly. They do not scatter much. They simply persist. Persistence is essential. Many particles in the early universe would not survive until today. They decay into lighter particles. They annihilate with their antiparticles. They thermalize and fade into the background. Dark matter needs staying power. It must last billions of years. The axion, because its interactions are so weak, and because it can be very light, can naturally be stable enough. That makes it a good relic. It is not only born early, it endures. The same weakness that makes it hard to detect also allows it to remain almost unchanged across cosmic history. A particle that rarely interacts is a particle that rarely gets disturbed. This gives the axion a peculiar kind of invisibility. It is not hidden because it is sealed away somewhere. It is hidden because it is too free. It passes through ordinary matter without much happening. It does not get absorbed, reflected, or scattered in ordinary ways. It is not trapped in atoms, not caught in chemistry, not gathered into glowing surfaces. It belongs to gravity more than to light. If axions were born in the early universe, then they have been travelling through the expanding cosmos ever since, forming enormous halos around galaxies and drifting through the spaces between stars, with almost no sign of their presence except the gravitational shape they help create. And perhaps they are here now. That thought is worth treating calmly, not as a dramatic revelation, but as a possibility. The same axion field whose motion began when the universe was young may be passing through Earth at this moment. It would pass through rock, oceans, buildings, and bodies almost completely unnoticed. In laboratories, scientists build devices to coax a tiny response from it, often by using powerful magnetic fields that might allow axions to become detectable light. But in everyday life, there is no sensation of this dark matter wind. There is only the ordinary room, the ordinary night, the ordinary breathing of the world. If axions exist, they are not elsewhere. They are part of the cosmic environment we already inhabit. This is one of the quiet pleasures of the Axion story. It connects beginnings to the present. The early universe is not simply a vanished era sealed behind time. Its processes left relics. The light of the cosmic microwave background still surrounds us. The abundance of hydrogen and helium still reflects early nuclear reactions. The distribution of galaxies still carries the imprint of tiny primordial fluctuations. If axions are dark matter, then they too are an ancient relic, a surviving trace of a field that began moving when the universe was a fraction of its current age, so tiny that ordinary language struggles to hold it. They would be old not just in years, but in origin, born from the changing conditions that turned the early fireball into the structured cosmos. The question of axion birth therefore leads naturally into the broader dark matter puzzle. It is one thing to say axions could have been produced. It is another to ask whether they could account for the missing mass we infer from galaxies, clusters, and the large-scale structure of space. To answer that, we have to step outward from the early universe and look at the evidence for dark matter itself. We need to see why the visible universe is not enough, why gravity keeps pointing toward an unseen component, and why a particle as quiet as the axion could be exactly the sort of thing the cosmos has been asking us to find. To understand why axions became so tempting, we need to step away from the very young universe for a while and look outward, into the slow turning of galaxies. This is where the dark matter puzzle first becomes visible, although visible is not quite the right word. Dark matter is known not because it shines, but because everything around it moves as though it is there. It is the unseen weight in the room. It is the missing mass in the dance of stars. It is the quiet gravitational presence that keeps appearing whenever astronomers measure the universe carefully enough. For most of human history, the night sky looked like a collection of bright points arranged on a dark background. Stars were the obvious things. Planets wandered among them. The moon changed its face. Comets appeared like unexpected guests, often causing people to become dramatic in ways that were understandable at the time. But the darkness between the stars seemed mostly empty. Even after telescopes revealed galaxies, nebulae, clusters, and the immense scale of space, it was natural to think that the bright things were the main things. Stars shine, so stars must be where most of the matter is. Gas clouds glow or absorb light so they can be counted. Dust blocks light, so it can be inferred. The universe seemed difficult, yes, but at least the stuff in it appeared to announce itself one way or another. Then gravity began telling a different story. Gravity is useful because it does not care whether something shines. A dark object with mass pulls just as surely as a bright one. A planet at night has gravity. A cold stone has gravity. A sleeping cat has gravity, though usually not enough to bend the path of light unless it has chosen to lie directly on your keyboard, which is a different kind of force entirely. If astronomers want to know how much mass is present in a system, they can look not only at what glows, but at how things move. Motion is a kind of confession. Stars orbit because gravity holds them. Galaxies gather because gravity draws them together. Light bends because gravity curves its path. If the visible matter is not enough to explain those motions, then something else must be contributing. One of the earliest hints came from galaxy clusters. These are vast gatherings of galaxies bound together by gravity. In the 20th century, astronomer Fritz Zwicky studied the Coma cluster and noticed that the galaxies inside it were moving too quickly. If the only mass present were the visible galaxies, the cluster should not have been able to hold together. The galaxies should have flown apart like people on a spinning fairground ride after someone has very unwisely removed the safety rail. Zwicky concluded that there must be much more matter present than could be seen. He called it dark matter, meaning matter that did not emit detectable light. At the time, the idea did not immediately transform astronomy. Partly that was because the measurements were difficult. Partly it was because Zwicky himself had a personality that did not always make his colleagues eager to agree with him over breakfast. Science is done by humans after all, and humans bring all their little weather systems with them. But the clue remained. Galaxy clusters seemed heavier than their visible matter suggested. Later, the evidence became much stronger through the study of individual galaxies. A galaxy like the Milky Way is a rotating system. Stars orbit the galactic centre, and gas clouds do too. If most of the mass were concentrated in the bright central regions, then stars far from the centre should move more slowly than stars closer in. This is similar to the way planets in the outer solar system orbit the Sun more slowly than planets closer to the Sun. But when astronomers measured the speeds of stars and gas in spiral galaxies, they found something unexpected. The outer regions were moving too fast. The rotation curves stayed flat, meaning the orbital speeds did not fall off as expected. This became one of the clearest signs that galaxies are embedded in much larger halos of invisible matter. The stars and gas we see are only the luminous part, like the bright foam on the surface of a much deeper wave. The dark matter halo extends beyond the visible edge of the galaxy, adding gravity and allowing outer stars and gas to move at the speeds we observe. Without that extra mass, the galaxy would not behave the way it does. This work became strongly associated with Vera Rubin and her collaborators, whose careful measurements helped make dark matter impossible to ignore. It is one of those moments in science where patience matters more than drama. The universe did not reveal the missing mass with a thunderclap. It revealed it through repeated measurements of stars moving around galaxies just a little too quickly for comfort. Once this pattern was seen, it appeared again and again. Different galaxies, different instruments, different methods, the same general problem. Visible matter was not enough. You could try to account for some missing mass with faint stars, cold gas, black holes, or planets drifting in the dark. Those things exist and they do contribute some mass. But they do not solve the whole puzzle. Ordinary matter has habits. It interacts with light. It forms atoms. It absorbs, emits, heats, cools, collapses, and leaves chemical and electromagnetic fingerprints. The missing matter behaves differently. It seems to be abundant, gravitationally important, and almost completely uninterested in light. Gravitational lensing provides another powerful clue. According to general relativity, mass bends the path of light. A large concentration of matter can act like a lens, distorting and magnifying the images of distant galaxies behind it. Astronomers can use these distortions to map where mass is located, whether or not that mass is shining. This is a wonderfully direct way to weigh invisible things. It is a little like seeing the shape of a glass, not by looking at the glass itself, but by watching how it bends the pattern behind it. When astronomers map galaxy clusters through lensing, they often find that most of the mass is not where the visible stars alone would put it. The gravitational field is stronger and more extended. In some dramatic systems, clusters have collided, and the visible hot gas has been separated from much of the gravitational mass. Hot gas can be seen in X-rays because ordinary matter collides, heats up, and slows down. Dark matter, by contrast, appears to pass through with much less interaction. The result is a separation between where most ordinary matter is and where most gravity points. This kind of observation strongly supports the idea that dark matter is not merely ordinary matter we fail to count. It behaves like a distinct component. There is also evidence from the oldest light we can observe, the cosmic microwave background. This light was released when the universe became transparent, long before stars and galaxies formed, it is not perfectly uniform. It contains tiny variations, warmer and cooler patches that reflect early density differences and the behaviour of matter and radiation in the young cosmos. By studying these patterns, cosmologists can infer the ingredients of the universe. The results point to a universe in which ordinary matter is only a small fraction of the total matter. Dark matter is far more abundant. It was present early, helping shape the gravitational wells into which ordinary matter later fell. This is an important part of the story. Dark matter is not just an extra ingredient added to fix galaxy rotation curves. It appears across many independent lines of evidence. Galaxies need it. Galaxy clusters need it. Gravitational lensing maps it. The cosmic microwave background points to it. The growth of large-scale structure depends on it. These clues come from different eras and different scales, from the ancient universe to present-day galaxies, from individual stars to clusters millions of light-years across. They all tell a similar story. There is more matter than meets the eye, and most of it is not made of the ordinary atoms that make stars, planets, and people. So what must dark matter be like? It must have mass, because gravity responds to it. It must be stable, or at least long-lived enough to survive from the early universe until today. It must not interact strongly with light, or we would see it directly. It must not interact strongly with ordinary matter, or it would have shown up in laboratory experiments and changed the behaviour of galaxies, stars, and gas clouds in ways we do not observe. It must have been produced in the early universe in the right amount. It must move slowly enough, in the broad cosmological sense, to allow galaxies and clusters to form. This set of requirements is strict, but not hopeless. It points toward new particles or fields beyond the standard model. For many years, one of the most popular possibilities was that dark matter might be made of heavy particles that interact weakly with ordinary matter. These candidates were attractive for several theoretical reasons, and many experiments were built to search for them. The search continues, but no confirmed signal has appeared. That does not mean heavy dark matter is impossible. It means the simplest hopes have been squeezed by experiment. As those searches have grown more constrained, attention has widened. Physicists have looked again at lighter candidates, hidden sectors, sterile neutrinos, primordial black holes, and axions. The dark matter problem is not short of suspects. It is more like a detective story in which everyone has a motive, nobody has a clear alibi, and the footprints are made of gravity. The Axion is especially interesting because it naturally fits many of the requirements. It would be stable or extremely long-lived. It would interact very weakly with ordinary matter and light. It could have been produced in the early universe through the motion of the Axion field. It could behave as cold dark matter, gathering gravitationally into halos around galaxies. And, as we have seen, it was not invented only for dark matter. It already had a job solving the strong charge and parity mystery. That gives it a seriousness that many speculative particles envy from across the room. If dark matter is made of axions, then the missing mass of the cosmos is not made of heavy invisible nuggets drifting through space. Instead, it may be made of an enormous number of very light particles, so numerous and coherent that their collective behaviour can resemble a field spread through the galaxy. The Milky Way would sit inside an axion halo. The Sun would move through it. Earth would move through it. Every laboratory detector would be carried through this invisible background as the planet turns and orbits. The axion dark matter would not feel like a wind because it would barely touch us. But in the language of detectors, scientists sometimes imagine Earth moving through a dark matter sea. That image helps explain how local and cosmic this question is at the same time. Dark matter is responsible for the structure of galaxies, yet if it exists in the expected way, it is also present in the room around you. Not densely in any ordinary sense, not as something you could scoop into a jar, but present as a gravitational and particle background. It passes through walls without noticing them. It passes through bodies without harm. It passes through detectors almost always without a signal. The challenge is to create conditions under which one tiny interaction becomes possible. one faint conversion into detectable light, one barely perceptible nudge in a carefully prepared instrument. This is why the search for Axion dark matter has such a different feeling from ordinary astronomy. Telescopes collect light. They look outward and gather signals that arrive from stars, galaxies, and the distant universe. Axion detectors often sit in laboratories, sometimes underground, listening for dark matter that may already be passing through them. The cosmic quarry is not distant, it is immediate. The difficulty is not travel, but sensitivity. The universe may be bringing dark matter straight through the experiment at every moment, and the experiment must be quiet and clever enough to notice. Dark matter also forces us to reconsider what we mean by normal. Ordinary matter feels normal because we are made of it. It makes rocks, oceans, trees, skin, clouds, books, and the bits of toast that somehow leave crumbs in places toast has never visited. It interacts with light, so it creates vision. It forms atoms, so it creates chemistry. It clumps into stars, so it creates heat and illumination. But in the cosmic accounting, ordinary matter is not the majority. It is the visible minority. The stuff that makes everything familiar may be only a small, bright fraction of the matter in the universe. Most matter may be dark, silent, and non-atomic. The word normal, in a cosmic sense, may be a rather local opinion. That thought can be unsettling, but it is also freeing. It reminds us that human intuition formed in a narrow environment. We evolved on a rocky planet, under a nearby star surrounded by matter that interacts richly with light and chemistry. Of course, that feels like the main kind of matter. It is the kind that made us. But the universe is not required to be built mostly from the ingredients that are convenient for biology. The cosmos may contain whole categories of matter that do not form bright objects, do not make surfaces, do not make sounds, and do not announce themselves except through gravity. Dark matter is not strange because it is impossible. It is strange because we are not made of it. The missing mass problem also shows how careful scientists must be before accepting a new substance. Could gravity itself be different on galactic scales? Some researchers have explored that possibility. Modified gravity ideas try to explain the observations without dark matter by changing the rules of gravity in very weak acceleration environments or across large distances. These ideas have had some success in describing certain galaxy rotation patterns, and they are important to consider because science should not ignore alternatives. But dark matter remains the leading explanation because it fits a wider range of evidence, especially galaxy clusters, gravitational lensing, the cosmic microwave background, and the growth of structure. It is not based on one awkward observation. It is woven through the whole cosmic dataset. Still, the exact nature of dark matter remains unknown. That uncertainty is the open door through which the Axion walks. It is not enough to say the universe has missing mass. We need to know what kind. Is it one particle or several? Does it have hidden interactions with itself? Was it born thermally from the early universe or through the motion of a field? Does it have a mass so small that it behaves like a wave across astronomical distances, or a mass large enough to behave like tiny invisible dust? Could different dark matter candidates contribute different fractions? These questions matter because each answer changes the story of cosmic formation and the strategy for detection. Axions provide a particularly elegant version of the dark matter story because their abundance can emerge from the early displacement of a field. The universe does not need to manufacture them in ordinary collisions and then leave just the right leftover amount. Instead, the Axion field begins away from its resting state, then starts moving as the strong force changes with cooling. The energy in that motion becomes Axion dark matter. This mechanism can naturally produce cold dark matter, depending on the Axion properties and early cosmic history. It is one of the reasons the Axion feels less like an invented patch and more like a thread pulled from a deeper fabric. If Axions form dark matter halos, They would shape galaxies in the same broad way other cold dark matter candidates do. They would provide the extra gravitational pull needed to explain flat rotation curves. They would help clusters remain bound. They would contribute to gravitational lensing. On large scales, they could help build the cosmic web, but on very small scales, depending on their mass, axions might produce distinctive effects. Extremely light axion-like particles could have wave behavior that smooths out small structures. The classic axion connected to the strong force usually occupies a different range, but the broader family of axion-like dark matter candidates gives physicists many possibilities to test. In this way, dark matter is not just a question of whether something exists, it is a question of texture. What kind of invisible structure does the universe have? The missing mass of the cosmos is therefore more than a bookkeeping problem. It is a clue about the hidden architecture of reality. The visible universe is shaped by something that does not shine. The earliest light carries the imprint of something that did not couple to light in the ordinary way. Galaxies rotate inside halos we cannot see. Clusters bend space-time with more mass than their glowing contents can provide. Every line of evidence tells us that our inventory is incomplete. The Axion is one of the most graceful attempts to complete it, because it begins with a puzzle in the strong force and ends as a possible ocean of dark matter surrounding every galaxy. There is a quiet irony in this. The Axion was proposed to explain why something inside the neutron is almost absent. Dark matter was proposed to explain why something around galaxies is strongly present. One mystery is about a missing effect, the other is about missing mass. The same particle could answer both. It could explain why the neutron is too balanced and why galaxies are too heavy. It could be the reason a tiny internal arrow is not seen, and the reason vast spiral galaxies do not fly apart. Few ideas in physics stretch so far with such a soft voice. As we follow this trail further, the next question becomes practical. If axions could be everywhere, if they could fill the halo of the Milky Way and pass through Earth constantly, why have we not found them? The answer is not that scientists have forgotten to look. They have looked, and they are looking with increasing care. The answer lies in the very nature that makes the axion useful. It is light, stable, and almost silent. It interacts so weakly that ordinary detectors are nearly blind to it. To find an axion, we cannot simply wait for a loud collision. We have to persuade it, under special conditions, to reveal itself as something we know how to measure. And that brings us toward the delicate difficulty of detection, where powerful magnets, cold cavities, quiet laboratories, and patient instruments try to hear the faintest possible signal from the dark. Finding an axion is difficult for almost the same reason an axion is attractive. It is expected to be quiet, not merely quiet in the ordinary sense like a person walking gently across a room, but quiet in a far deeper physical sense. If axions exist, they would barely interact with the matter and light that make up our usual instruments. They could be flowing through Earth, through laboratories, through mountains, oceans, walls, and sleeping cities, and almost nothing would happen. No spark, no flash, no little ping in a detector that politely announces that a mystery has arrived. The axion is not hiding behind a distant star or tucked away at the edge of the observable universe. It may be everywhere around us. The problem is that it's almost perfectly indifferent to being noticed. This is a strange kind of difficulty. In many searches, the challenge is distance. A galaxy is far away, so we build a bigger telescope. A planet is dim, so we gather more light. A cell is small, so we use a microscope. But with axions, the challenge is not simply that they are far, faint, or tiny. It is that they are weakly connected to the parts of reality we know how to touch. Ordinary matter is chatty. Electrons respond to electric fields. Atoms absorb and emit light. Molecules collide, heat up, glow, vibrate, and form all the busy chemistry of the visible world. Axions, by comparison, would pass through this lively conversation like someone drifting silently through a crowded station without brushing anyone's sleeve. This weak interaction is not a small inconvenience, it is central to the whole story. If axions interacted strongly with ordinary matter, they would not be good dark matter candidates. They would have been seen already, or they would have changed the behaviour of stars, galaxies and laboratory experiments in obvious ways. Dark matter must be present gravitationally, but mostly absent electromagnetically. It must have weight but not shine. It must shape galaxies but not gather into bright clouds or ordinary atoms. The axion fits that personality because it is expected to interact so faintly. But that means the very property that allows it to hide in the cosmos also makes it hide from us. Imagine trying to detect a snowflake falling into the ocean during a storm, except the snowflake does not splash, does not melt, and is not entirely sure it wishes to be a snowflake. That is not a perfect analogy, but it gives a sense of the mood. An axion signal, if it appears, would be tiny compared with the noise of the ordinary world. Every detector exists inside a universe full of disturbances. Thermal motion creates background noise. Electronics create noise. Radio signals leak in from human technology. Cosmic rays pass through. Materials contain tiny impurities. Even the detector itself, by being made of matter at a non-zero temperature, produces restless motion. The axion signal must be separated from all of that. It is like trying to hear a single distant flute while someone next door is rearranging furniture. The kettle is boiling and a refrigerator has decided to hum with artistic commitment. One of the main hopes for detecting axions comes from their possible relationship with light. Under the right conditions, especially in a strong magnetic field, an axion may convert into a photon, which is a particle of light. This is not light in the ordinary visible sense necessarily. Depending on the kind of axion and its mass, the photon could appear as a microwave signal or as higher energy radiation. The important point is that light is something we know how to detect. If axions barely speak to ordinary matter, we try to place them in a situation where they might whisper into a language our instruments understand. Strong magnetic fields become part of that translation. Experiments such as the Axion dark matter experiment use a strong magnetic field and a tuned cavity to try to convert dark matter axions into detectable microwave photons, while solar axion searches use magnetic fields to look for axions from the sun converting into detectable light. But even this clever trick comes with a problem. We do not know the axion's mass. That may sound like a technical detail, but it controls much of the search. If you do not know the mass, you do not know the precise energy of the signal you are looking for. In some experiments, that means you do not know the frequency to which the detector must be tuned. The search becomes something like scanning a vast radio dial for a station that may be broadcasting almost unimaginably softly. You cannot simply listen everywhere at full sensitivity at once. You tune, wait, measure, shift slightly, and tune again. The process is patient, repetitive, and delicate. CERN describes this kind of resonator search as essentially a radio that must be slowly tuned because the Axion radio station is not known in advance. This makes Axion hunting very different from looking for a loud, dramatic event. Some particle detectors are built to catch collisions. A particle enters, strikes something, and leaves a burst of energy, a track, or a flash. Axions may not behave that way. For many possible axion masses, the expected dark matter signal is not a sudden crash but a faint, steady tone. It may sit in the data as a narrow excess at one frequency, buried under statistical noise. Finding it requires not only sensitive instruments, but also careful confidence. A scientist must ask whether a small bump is real, or whether it is a fluctuation, an interference signal, a vibration, a thermal feature, or the ghostly influence of some piece of equipment behaving badly, because equipment has moods too, even if engineers prefer not to say so. Temperature is another enemy, heat is motion, and motion creates noise. If the signal you seek is extraordinarily small, ordinary thermal agitation can cover it. That is why many Axion experiments are cooled to extremely low temperatures. Cooling quiets the detector. It reduces the random background created by jiggling atoms and noisy electronics. The colder and quieter the experiment becomes, the better the chance of hearing something faint. This is one of the lovely ironies of modern physics. To search for a particle that may fill the galaxy, scientists build instruments that are almost unbelievably cold, shielded, and still. The cosmos may be vast, but the search often happens inside a metal chamber where the main goal is to make everything stop fidgeting. Even after cooling, the detector must be protected from ordinary human noise. We live inside a fog of electromagnetic chatter. Phones, wireless networks, radio broadcasts, power lines, screens and electronics all fill the environment with signals. To an Axion detector, these can be like loud conversations in the hallway outside a room where someone is trying to hear a moth land on velvet. A false signal can appear if a device leaks radio frequency noise into the apparatus. A tiny imperfection can mimic the kind of excess researchers hope to find. So experiments use shielding, careful design, repeated checks, and independent confirmation. The quieter the signal, the more suspicious scientists must be. In Axion physics, skepticism is not a bad mood. It is part of the instrument. The size of the search space is another challenge. The Axion is not one single target with a known address. Its possible mass and interaction strength can occupy a broad range. Different theories suggest different possibilities. Some axions would be easier to detect but are already ruled out. Others remain possible but demand more sensitive methods. Some would produce microwave signals in one range, others would require different devices entirely. Some may be better searched for as dark matter in our galaxy. Others may be searched for as particles produced in the sun. Still others may reveal themselves through tiny effects in precision experiments. The result is not one search, but a whole landscape of searches. That landscape is sometimes called parameter space, which is a tidy phrase for a rather untidy reality. It means all the possible combinations of Axion properties that might exist. Mass, interaction strength, origin, abundance, and connection to other particles all matter. Experiments can only explore part of this landscape at a time. When they find nothing, that does not simply mean failure. It means a region has been searched and constrained. The map becomes clearer. The possible hiding places shrink. This is slow science, but it is real progress. A null result can be valuable because it tells us where the Axion is not, or at least where it is not with certain properties. The darkness becomes a little less undefined. There are different styles of Axion searches because axions, if real, may appear in different contexts. Dark matter haloscopes look for axions that already exist as part of the dark matter halo surrounding the Milky Way. The word halos comes from the idea that galaxies are embedded in broad invisible clouds of dark matter extending beyond their visible stars. A haloscope tries to detect the local dark matter passing through the laboratory. The Axion dark matter experiment is one example, using a strong magnet, a cavity, and extremely sensitive low-noise electronics to listen for microwave photons produced by Axion conversion. Helioscopes, by contrast, look toward the sun. If axions are produced inside the hot solar interior, they could stream outward and pass through Earth. A helioscope uses a strong magnetic field to try to convert those solar axions into detectable photons. The CERN Axion Solar Telescope used a powerful magnet pointed toward the sun for this purpose, and future observatories such as the International Axion Observatory are designed to extend this idea with larger and more specialized equipment. These approaches are complementary, because they are not looking for exactly the same thing in exactly the same way. A dark matter search asks whether axions make up the invisible matter around our galaxy. A solar search asks whether axions are produced in stars through their interactions with ordinary particles and light. Precision laboratory experiments ask whether axion fields create tiny changes in atomic or nuclear behavior. The axion may leave no footprint in one place and still be visible in another. or it may leave no footprint anywhere we have searched so far because its properties lie beyond present sensitivity. This is why the field needs many instruments, not one heroic machine standing alone with a cape. The unknown mass also affects the size and design of experiments. A resonant cavity works best when its physical size matches the kind of signal expected. For some Axion masses, that size is manageable. For others, it becomes inconveniently large or small. Scientists then develop different methods, using circuits, materials, magnetic systems, optical cavities, or quantum sensors. Each method covers a different region of possibility. Searching for axions is not like building one telescope and pointing it at the sky. It is more like inventing a whole family of musical instruments, each designed to hear a different possible note from an orchestra that may or may not be playing. Then there is the issue of coherence. If Axion dark matter behaves like a field, it may produce a signal with a certain regularity, but that regularity is not perfect forever. The dark matter particles in the galaxy have a range of speeds. Earth moves through the galaxy, the Sun moves around the galactic centre, the planet rotates. All of these motions can slightly broaden or shift the signal. This is helpful in some ways because it gives scientists expected patterns to look for, but it also complicates the analysis. A real signal must fit what dark matter should do, not merely appear as a random bright spot in the data. Researchers need to ask whether a candidate signal changes with time, whether it appears again, whether it survives checks, and whether it can be explained by ordinary causes. The weakness of the Axion's coupling also means that bigger and stronger often help, but only with great difficulty. A stronger magnetic field can improve conversion. A larger volume can allow more axions to participate. A quieter amplifier can reduce noise. A longer observing time can improve confidence, but each improvement is hard-won. Strong magnets are expensive and technically demanding. Large cold volumes are challenging to maintain. Low-noise quantum electronics require great care. Shielding must be meticulous. Every gain in sensitivity may require years of development. The search for axions is a reminder that progress in fundamental physics often depends not only on grand ideas, but on plumbing, wiring, refrigeration, machining, calibration, and the quiet heroism of people who know exactly which cable is causing the problem. There is also the difficulty of distinguishing discovery from desire. The axion is a beautiful idea. It solves a real theoretical problem. It could explain dark matter. It appears naturally in several broader theoretical frameworks. Scientists are human, and a beautiful idea can be tempting. But the more tempting an idea is, the more carefully it must be tested. A faint signal cannot be accepted simply because it would be lovely if it were true. It must survive repeated measurement, independent confirmation, and every boring explanation researchers can think of. In this sense, the difficulty of finding axions is not only technical, it is intellectual. The search requires patience without gullibility, hope without haste. This is one reason the absence of detection so far has not killed the idea. Axions can hide in many plausible regions that experiments are only beginning to explore with the needed sensitivity. Earlier experiments ruled out louder versions. Newer ones are entering quieter territory. Some searches have reached sensitivities where important theoretical models can be tested. Others are extending the range of possible masses. The field advances not by one dramatic leap, but by widening and deepening the search. It is less like kicking down a door and more like carefully checking every drawer in an enormous old house, including the drawer that contains only batteries, one button, and a mysterious key nobody remembers owning. The difficulty is sharpened by the fact that axions may not make up all of dark matter. They could be a fraction, or the original axion could exist but be too rare to account for the full missing mass. Or dark matter could be made of several components, with axions as one member of a darker family. This possibility makes interpretation more subtle. A non-detection in one experiment may rule out axions as all of dark matter in a certain range, but not rule out axions entirely. It may limit the strength of their interaction, their abundance, or their mass. The language of exclusion and constraint becomes careful, because the universe has many ways to remain inconvenient. Even the word detect hides layers. To detect an axion directly, one usually means observing a signal caused by axions interacting in a controlled experiment. But there are also indirect hints, astrophysical limits, stellar cooling arguments, and cosmological constraints. Stars can act as particle laboratories. If axions are produced too efficiently in stellar interiors, they could carry away energy and change how stars evolve. Observations of stars therefore restrict how strongly axions can interact. Supernovae, white dwarfs, red giants, and other astrophysical systems all provide clues. These are not simple direct detections, but they shape the allowed possibilities. The cosmos itself becomes a detector, though one with rather poor labelling and no convenient instruction manual. This astrophysical side adds another reason the search is hard. Axions must be weak enough to have escaped detection and not disrupt known astrophysics too much, but strong enough for experiments to eventually see. The allowed region can be narrow, or at least difficult to reach. It is a balance between invisibility and accessibility. Too visible, and the axion would already have been found or ruled out. Too invisible, and it becomes nearly impossible to test. The most interesting axions live in the twilight between those extremes, where they may be real, important, and just barely within reach of human instruments. There is a calm lesson in this. We often expect discovery to come from seeing something bright, a new planet crossing a star, a new particle leaving a track, a new galaxy glowing at the edge of time, but axion discovery may come from recognizing a tiny excess after months or years of scanning, then checking it again and again until every ordinary explanation has been exhausted. It may first appear as a faint line in a spectrum, a small response in a resonator, or a subtle pattern repeated with the patience of the Earth's motion through the galaxy. The announcement, if it comes, may not feel dramatic at first glance. It may look like a careful plot, a confidence level, a set of controls, and a room full of physicists trying very hard not to smile too soon. The search also depends on knowing how to listen. The axion is difficult to find because it is not trying to be found in the ways ordinary particles are. It does not crash into detectors often. It does not light up the sky. It does not form atoms. It does not sit in jars. It may be a field oscillating through space, converting only rarely into detectable light under special conditions. That means experiments must be tuned, shielded, cooled, and interpreted with extraordinary care. The detector becomes a question shaped in metal, magnetism, and silence. It asks the same thing over and over. Are you there? Are you there? Are you there? And if the answer is not yet, the question continues. This is not failure. It is the nature of searching for something whose existence is plausible but not guaranteed. Every improvement narrows the unknown. Every non-detection sharpens the map. Every new technique opens a region that was previously inaccessible. The axion remains difficult because it belongs to a category of reality that does not participate much in our ordinary senses, but that is exactly why it could matter so much. A particle that barely interacts can survive from the early universe. A field that barely speaks can fill a galaxy. A whisper can carry the weight of stars if the universe is built that way. So the difficulty of finding axions is not a side note, it is part of their identity. They are expected to be light, weak, stable, and subtle. They may be abundant but nearly silent. They may pass through everything and leave almost nothing behind. To find them, scientists must turn the world down. They must quiet heat, shield noise, tune instruments, strengthen magnets, and wait for a signal that may be less like a knock at the door and more like a single note heard through a wall. That is where the next part of the story naturally leads, into the experiments themselves, where laboratories become listening rooms for dark matter, and human patience is shaped into devices designed to hear the invisible. To listen for axions, scientists have had to build a very unusual kind of instrument. Not a telescope in the ordinary sense, with a mirror pointed toward the sky. Not a particle detector waiting for a bright collision to leave a dramatic trail. Not a camera, not a net, not a jar placed hopefully beneath the cosmic shelf. An Axion experiment is closer to a listening room. It is a carefully quiet space where magnetism, cold metal, sensitive electronics, and patient analysis are arranged around one delicate question. If the dark matter is passing through us all the time, can we persuade one tiny part of it to become something visible? That word persuade is not too far from the truth. Axions, if they exist, are not expected to collide with ordinary matter very often. They do not behave like little stones striking a window, so the cleverness of many experiments lies in using a special interaction that the axion may have with light. In the presence of a strong magnetic field, an axion may turn into a photon, and a photon is something we know how to detect. It may not be visible light, it may be microwave radiation, it may be an X-ray, it may be a single faint signal appearing inside equipment cooled until the ordinary noise of heat has nearly gone silent. But once an axion becomes a photon, however rarely, the hidden has translated itself into a language instruments can understand. One major family of experiments searches for axions that may already be drifting through the laboratory as part of the dark matter halo of our galaxy. These experiments are often called heloscopes because they look for dark matter from the halo surrounding the Milky Way. The idea is simple in outline and extremely difficult in practice. Put a carefully designed detector inside a powerful magnetic field. Tune it to the kind of signal an axion of a certain mass would produce. Wait. Listen. Adjust the tuning. Wait again. The Axion dark matter experiment at the University of Washington is one of the best-known examples. It uses a strong magnetic field, a microwave cavity, and very sensitive low-noise quantum electronics to search for dark matter axions converting into microwave photons. The microwave cavity is at the heart of this kind of search. You can imagine it as a metal chamber that prefers to ring at certain frequencies, a little like how a bottle gives a note when air moves across its opening, though in the detector the ringing is electromagnetic rather than musical. If the cavity is tuned to the right frequency, and if axions of the matching mass are passing through the magnetic field, their conversion into photons can be enhanced. The signal would be tiny. Not merely small, but tiny in the way a candle is tiny compared with a sunrise seen from orbit. So the whole experiment must be made quiet. The cavity is cooled, the electronics are refined, the data are examined for a faint excess that could be the dark matter field humming at just the right pitch. This is why Axion experiments often feel less like catching a creature and more like tuning a radio. Nobody knows exactly where the station is. The station may be broadcasting softly, it may be hidden under static, and the dial is very large. So researchers move step by step through possible frequencies, looking for a signal that rises above the noise. A false bump can come from ordinary interference. A stray radio signal, a vibration, a quirk in the electronics, or some small imperfection can imitate something interesting for a moment. The detector has to be tested, retested, and understood so well that a possible discovery is not simply a bump that everyone wishes were true. It must survive suspicion. The patience involved is extraordinary. In ordinary life, if you spend hours listening to static, people may begin to worry about you. In Axion physics, this becomes a career, though with better equipment and more graphs. The experiment scans a little region of possibility, then another, then another. A null result is not wasted time. It draws a line on the map. It says that if axions exist in this range, they do not interact strongly enough to have appeared here, or they are not all of the dark matter in this way. The darkness becomes slightly less vague. The search narrows, not by finding the answer immediately, but by learning where the answer is not. Another family of experiments looks not for dark matter axions already around us, but for axions that might be produced in the sun. The sun is a vast natural furnace, full of hot plasma, strong electromagnetic fields, and energetic particles. If axions couple to light, then processes inside the Sun could create them. Because axions interact so weakly, they could stream out of the solar interior almost unhindered, passing through the outer layers and crossing space toward Earth. We would not see them directly, but an experiment can point a powerful magnet toward the Sun and try to convert those solar axions back into photons. The Axion Solar Telescope, known as CAST, used this approach with a strong superconducting magnet and X-ray detectors, relying on the magnetic field to convert possible solar axions into X-rays that could be recorded. This kind of experiment is called a helioscope, from the idea of looking at the Sun. But it is not looking in the ordinary optical way. It is looking for something the Sun might be sending silently through matter and space. The magnet follows the Sun for part of the day, gathering data when aligned with it, and then background measurements are made when it is not pointed at the Sun. The comparison matters. If a signal appears only when the magnet is tracking the Sun, and if it has the right properties, that would be far more interesting than a signal that appears randomly at tea time, because someone nearby switched on a piece of equipment with poor manners. CAST did not discover axions, but it set important limits. That is often how science moves in the dark. An experiment searches, finds no confirmed signal, and still changes what remains possible. It tells future experiments how much farther they must go. It sharpens the requirements. It helps rule out axions that would have interacted too strongly with light. In that sense, even silence can be productive. The next generation idea, the International Axion Observatory, is designed as a much more powerful helioscope, with a purpose-built magnet system, X-ray optics, and low background detectors intended to improve the search for solar axions. There is something charming about the difference between a heloscope and a helioscope. One sits quietly and listens for the dark matter passing through the laboratory from the galaxy around us. The other turns toward the Sun, waiting for axions that might be born in the solar core. One searches the local dark sea, the other listens to a star. Both use magnetic fields as translators. Both depend on the faint possibility that an axion can become a photon. Both are, in their own way, attempts to make the invisible introduce itself. Then there are experiments with an even more storybook-sounding design, often called light shining through a wall. The idea sounds like something a magician would promise at a village fair, shortly before producing a tired rabbit from a hat. But the physics is serious. In such an experiment, scientists send a strong laser beam into a magnetic field. If axion-like particles exist and couple to light, a tiny fraction of the photons in the beam could convert into these particles. Then comes the wall. Ordinary light cannot pass through it. But axion-like particles, interacting very weakly, could pass through almost as though the wall were not there. On the other side, another magnetic field could convert some of them back into photons. If light is detected beyond the wall, in a carefully shielded region where ordinary light cannot have reached, that could be evidence for a new particle. The Alps. To experiment at DZ in Germany uses this light shining through a wall concept to search for axion-like particles and other very weakly interacting particles. The elegance of this method is that it does not require axions to already exist as dark matter in the laboratory. The experiment tries to create and detect axion-like particles in a controlled setup. It is a laboratory question from beginning to end. Light enters. Something invisible may be made. The invisible passes through a barrier. Light may return. It is wonderfully direct in concept, even if the technical execution is anything but simple. The expected signal can be incredibly rare, so the apparatus must keep ordinary stray photons away with almost obsessive care. The detectors must know the difference between a real regenerated photon and the tiny background events that appear in any sensitive measurement. It is less a magic trick than a test of whether nature has hidden a small doorway between light and a nearly invisible field. The name axion-like particle is important here. Not every experiment is searching only for the original axion that solves the strong force mystery. Some are searching for broader cousins, particles that resemble axions in having weak interactions with light, but may not have exactly the same origin. The original axion has a special connection to the strong charge and parity problem. Axion-like particles are a wider family. They appear in many theories beyond the standard model, and some could be dark matter, while others might simply be new light particles. This broader search matters because nature may not provide only the simplest answer. It may provide relatives, variations, or a whole hidden sector quietly attached to the known world. Other experiments listen in still different ways. Some use atoms or nuclei as tiny sensors. If an axion field passes through matter, it might cause extremely small oscillations in nuclear properties or spin behavior. The effect would be so faint that it requires precision measurement of the most delicate kind. These experiments do not look for a photon appearing in a cavity or an X-ray from the sun. They look for tiny periodic changes in systems that can be measured with exquisite care. In this style of search, the detector becomes almost like a clock or compass, sensitive to a dark matter background. It asks whether the axion field is gently nudging the quantum properties of matter as Earth moves through the galaxy. There are also proposals using special materials. In some materials, electrons and light behave collectively in ways that may enhance sensitivity to axions in mass ranges that are difficult for traditional cavities. Other designs use networks of sensors, resonant circuits, superconducting devices, or carefully arranged magnetic materials. The reason for this diversity is that axions could occupy many possible masses, and no single experiment can search all of them at once. A cavity may be excellent for one range. A material-based detector may be better for another. A helioscope explores solar production. A light shining through a wall experiment tests laboratory conversion. The whole field becomes a coordinated listening effort, with different instruments tuned to different possible voices. This is where the search becomes almost musical. If dark matter axions form a coherent field, they may produce an extremely narrow signal, a note determined by their mass and broadened slightly by their motion in the galaxy. The job of the experiment is to tune itself to that note, but because the note is unknown, the orchestra of detectors must cover many ranges. Some listen low, some listen high, some listen for solar X-rays, some listen for microwaves, some listen for changes in nuclear spin. Some try to make the particle in the laboratory and bring it back through a wall. None of them alone hears the whole possible song. Together they gradually reduce the silence. The darkness in these experiments is not only literal, though sometimes it is very literal indeed. Detectors are shielded from light, from radio noise, from cosmic rays, from heat, from vibrations, and from the clutter of human technology. But the deeper darkness is informational. We do not know the axion mass. We do not know how strongly it couples to light or matter. We do not know whether it makes all of the dark matter, some of it, or none of it. We do not know whether the original axion exists, or whether only axion-like particles exist, or whether nature chose an entirely different answer. The experiments operate inside that darkness, not by guessing wildly, but by making the unknown measurable one region at a time. A discovery would have to pass through many layers of caution. Suppose a haloscope sees a small signal at one frequency. The first response would not be celebration with confetti and a dramatic soundtrack. It would be checking. Does the signal persist? Does it appear when the magnet is on and disappear when conditions change? Can it be reproduced? Could it be a radio leak? Could it be a thermal fluctuation? Could some piece of hardware be responsible? If the signal survives, another experiment would need to confirm it, perhaps with a different design. Only then would the excitement become sturdy. Physics has learned, sometimes painfully, that nature is subtle and equipment is mischievous. A good discovery must be stronger than wishful thinking. If a solar helioscope saw an excess of X-rays while tracking the sun, similar suspicion would follow. Is the pointing understood? Is the background stable? Are the detectors behaving? Does the energy of the signal match expectations? Can ordinary solar physics explain it? If a light shining through a wall experiments or photons beyond the barrier, researchers would ask whether any ordinary light leaked through, whether the detector produced dark counts, whether the timing and alignment were correct. Every possible mundane explanation must be invited in, questioned, and politely shown out before new physics is allowed to sit down. There is a kind of beauty in that caution. The experiments are designed to listen for one of the most mysterious possible particles in the universe, but the daily work is often practical, methodical, and deeply grounded. Check the temperature, calibrate the amplifier, understand the magnet, measure the background, repeat the scan, look for interference, improve the shielding. There is no shortcut around this. The universe may be elegant, but detectors are built with bolts, wires, cryogenic systems, mirrors, cavities, vacuum chambers, and software. Discovery depends on the marriage of cosmic imagination and very careful maintenance. The people building these instruments are trying to measure something that may connect the strong force, dark matter, stellar interiors, and the early universe. Yet the path to that knowledge may involve lowering noise by a small amount, improving a cavity tuning mechanism, reducing detector background, or understanding one stubborn source of vibration. That is not less grand. It is how grand things become real. The bridge from theory to discovery is often made of ordinary details handled extraordinarily well. The experimental search also tells us something about the personality of modern physics. The largest machines are not the only path forward. Particle colliders remain powerful tools, but axions invite smaller, quieter, more specialized experiments. Some fit inside laboratories rather than sprawling across borders. Some use technologies borrowed from quantum information, radio astronomy, condensed matter physics, cryogenics, and precision measurement. The Axion has encouraged a kind of experimental creativity, because no one method is enough. When the target is subtle, imagination becomes part of the apparatus. This wide search is still ongoing. No confirmed Axion discovery has been made. That statement is important. The story remains open. But the absence of discovery so far is not empty. It has shaped the field, ruled out simpler possibilities, and pushed experiments into more sensitive territory. Each new search asks the question in a slightly different accent. Are axions the dark matter in the halo? Are they produced in the sun? Can light turn into them and back again? Do they nudge atomic systems? Do they hide in a mass range we have not yet reached? The answer may be no in one region and yes in another. Or it may be no everywhere, forcing physicists to look for a different hidden ingredient. Either outcome teaches us something. If axions are found, the consequences would be enormous. A signal in a dark matter haloscope would suggest that the invisible mass of our galaxy is not merely an abstract gravitational component, but a real field made of specific particles. A solar axion discovery would reveal new physics in the heart of stars. A laboratory regeneration signal would show that light can slip into a hidden particle state and return. Any of these would open a new window onto physics beyond the standard model. It would not be the end of the story. It would be the beginning of a more detailed one. What is the exact mass? How strong are the interactions? Does this particle solve the strong force mystery? Does it make all of the dark matter? Are there related particles? The first discovery would turn the axion from a possible answer into a new subject. And if axions are not found in the ranges we can test, that too matters. Theories must adapt. Other dark matter candidates gain ground. The strong force mystery remains, perhaps pointing to a different mechanism. The map changes. Science is not only the art of finding what one hopes to find, it is the art of letting reality narrow the possibilities, even when it does so quietly. In that way, axion experiments are not waiting passively in the dark. They are actively carving shape into the unknown. So when we say scientists are listening for axions, we mean something very literal and something more than literal. They are tuning resonators, watching detectors, pointing magnets at the sun, sending light toward walls, cooling cavities, and measuring faint signals. But they are also listening to the structure of the theory, to the silence of the neutron, to the rotation of galaxies, to the ancient evidence for dark matter, and to the possibility that all these clues belong to one story. The experiments are where that story meets the stubborn material world. They are the place where an elegant idea must become a signal or accept the discipline of remaining unseen. There is a quiet drama in that, not the drama of explosions or flashing screens, but the drama of patience. Somewhere, in a laboratory chilled almost to stillness, a magnet is waiting. A cavity is tuned. A detector is watching for a photon that should not be there unless an axion has passed through and changed its form. Somewhere else, a telescope magnet follows the sun, asking whether the star is sending particles no ordinary eye can see. At another site, a laser strikes a wall that light cannot cross, while instruments on the far side wait for the impossible to become faintly possible. All of these efforts share the same hope, that the darkness is not empty, that it has a particle, that with enough care, enough quiet, and enough time the universe may answer in a whisper. The next question is what such an answer would mean. An axion would not be just another particle added to a list. It would change how we understand symmetry, dark matter, the early universe, and perhaps the hidden structure of physical law. It would show that a tiny puzzle inside the strong force was connected to the largest invisible structures in the cosmos, and that the dark matter around galaxies may have begun as the motion of a field settling into balance when the universe was young. That possibility leads us beyond the detectors themselves and back toward the deeper meaning of the search, toward what axions could reveal about reality if the long listening finally hears something. If the long listening ever does hear an axion, it would not simply add one more name to the particle family. Physics already has a fair number of particles, and most people are not wandering around feeling that their lives lack one more item in a table. The importance of the axion would come from what it connects. It would join a puzzle inside the neutron to the invisible weight of galaxies. It would show that a tiny symmetry question in the strong nuclear force was not a minor technical irritation, but a signpost pointing toward a hidden field spread across the universe. It would mean that the darkness around galaxies is not just an absence of light, but a substance with a story, an origin, and a role in the deepest structure of physical law. That is why axions matter so much. They sit at a crossroads. One road leads inward, into the dense hidden world of quarks and gluons, where the strong force binds matter together. Another road leads outward, into the great halos of dark matter that surround galaxies and guide the growth of cosmic structure. Another leads backward in time, into the early universe, when fields settled, symmetries changed, and the ingredients of the cosmos took their modern form. Another leads into the future of experiment, where quiet devices cooled nearly to stillness try to detect signals so faint that ordinary intuition has no comfortable place to put them. If axions are real, those roads are not separate. They are parts of the same map. The first thing an axion would reveal is that symmetry is not just an elegant idea humans invented to make physics look tidy. It would show that symmetry can act as a deep organizing principle, one powerful enough to solve a mystery that otherwise looks like an unnatural coincidence. The strong nuclear force seems to avoid a certain kind of charge and mirror imbalance with astonishing precision. Without the axion, that quietness is difficult to explain. With the axion, the quietness becomes the result of a physical process. A field settles into a state where the unwanted imbalance disappears. Nature would not have chosen silence by accident. It would have a mechanism for becoming silent. This would be a profound lesson. The universe often looks messy on the surface. Stars explode, galaxies collide, planets are battered by impacts. Biological life is a long experiment in improvisation, with knees. But beneath that mess, physical law can contain very strict patterns. Symmetries tell particles how to behave, what can transform into what, and which processes are allowed. broken symmetries explain why the world has structure instead of perfect sameness. If the Axion exists, it would be another example of how a hidden symmetry, not obvious in ordinary life, can shape what matter is allowed to do. The neutron would become a quiet messenger from a deeper layer of order. It would also change how we think about dark matter. At the moment, dark matter is known mainly by its gravity. We infer it from the motion of stars, the behaviour of galaxy clusters, the bending of light, and the pattern of the oldest radiation in the universe. But we do not yet know what it is. If axions are found and shown to make up dark matter, then the missing mass would stop being only an accounting problem. It would become a physical field with identifiable properties. We could ask its mass, how it interacts, how it was produced, how it moves through the galaxy, and whether it forms subtle structures of its own. Dark matter would become less like a shadow in the equations, and more like a new medium filling the cosmos. That would be a major change in perspective. The visible universe is made of atoms, and atoms are wonderfully busy. They make stars, planets, dust, water, air, bodies, tea, and the occasional biscuit that disappears under suspicious circumstances. Dark matter does not appear to do any of that. If it is made of axions, then most matter in the universe may be something radically unlike the matter that makes familiar objects. It would not form atoms. It would not shine. It would not take part in ordinary chemistry. It would not make surfaces or smells or colours, yet it would provide the gravitational scaffolding on which galaxies formed. The matter we know would be the bright decoration on a darker foundation. That thought is not only scientific, it is also humbling. We tend to treat the world we touch as the main world. This is reasonable. We have hands, eyes, lungs, appetites, and schedules. Ordinary matter is the matter that matters to us most directly. But cosmology keeps reminding us that human familiarity is not the same as cosmic importance. The universe may be mostly built from things that do not notice us, do not interact with us, and do not reveal themselves except through patience and gravity. If axions are dark matter, then reality is not centered on what shines. Light becomes the exception, not the rule. The luminous cosmos would be the part that speaks loudly enough for creatures like us to hear. Axions would also reveal something important about the early universe. Dark matter had to come from somewhere. It did not simply appear around galaxies after the galaxies were already made. It was present early enough to influence how structure grew. If axions are the dark matter, then their origin may lie in the motion of a field that began displaced from its resting state, and later settled as the universe cooled. That would mean today's galaxies carry the memory of a field movement from the first moments of cosmic history. The rotation of stars in a spiral galaxy would be connected to the ancient behaviour of a field tied to the strong force. The past would not be gone, it would be stored gravitationally in the shape of the universe. This is one of the great themes of cosmology. The early universe did not vanish without a trace. It left relics. The cosmic microwave background is a relic light. The abundance of hydrogen and helium is a relic of early nuclear reactions. The distribution of galaxies is a relic of tiny initial density variations amplified by gravity. Axion dark matter would be another relic, not made in the same way as ordinary atoms, but preserved as a quiet field population across billions of years. If discovered, it would let scientists read another page of the cosmic record. It would tell us what kinds of fields existed when the universe was young, how they settled, and how hidden physics became visible through gravity. The axion would also deepen the idea that fields are more fundamental than particles in modern physics. In everyday language, particles sound like little objects, tiny specks with edges. But in quantum field theory, particles are excitations of fields. The field is the underlying thing, the particle is the ripple. If axions are found, they would be evidence for a new field spread through space. That field would not be a metaphor. It would be part of the furniture of reality, although furniture is perhaps too solid a word for something that passes through walls without asking permission. The discovery would remind us that empty space is not empty in the simple sense. It is filled with fields, possibilities, fluctuations, and hidden structure. This matters because much of the universe may be field-like in ways that our senses cannot grasp. We are comfortable with the electromagnetic field because it gives us light, radio, magnetism, warmth, and the ordinary electrical behaviour of matter. But other fields may exist with much quieter signatures. The Higgs field, for example, is already part of confirmed physics, giving mass to elementary particles through its constant presence. An Axion field would add another invisible background, one that solves a strong force puzzle and may provide dark matter. Reality would become less like a collection of things sitting in space, and more like a set of overlapping fields whose excitations sometimes appear as particles, forces, and matter. An Axion discovery could also point toward physics beyond the Standard Model. The Standard Model is extraordinarily successful, but it is not complete. It does not include gravity in quantum form. It does not explain dark matter. It does not fully explain why there is more matter than antimatter. It does not explain all the patterns in particle masses or why there are 3 families of matter. It leaves open why the strong force is so quiet in the charge and parity sense. The Axion would be one confirmed crack in the wall, a sign that the known theory is part of a larger structure. It would not overthrow the Standard Model. More likely, it would extend it. But that extension would be precious, because confirmed new particles are rare, and each one gives physicists a new handle on deeper laws. The Axion might also offer clues about higher energy physics that we cannot reach directly. Particle colliders can probe remarkable energies, but the early universe and deeper theoretical structures may involve scales far beyond current machines. Sometimes low energy, delicate measurements can reveal traces of very high energy physics. The Axion is exactly the sort of particle that could do this. Its properties might encode information about a symmetry broken at a very high scale, far beyond direct experimental access. In that sense, a tiny signal in a cold laboratory could become a message from physics, otherwise hidden behind enormous energy barriers. We would not be smashing our way up to that scale. We would be listening to its echo. There is also a connection to broader theories, including some versions of string theory and other attempts to unify the forces. These ideas often predict many light fields resembling axions. Some physicists even speak of an axion landscape, a family of related particles with different masses and interactions. That phrase can sound a little grand, and it remains speculative, but the general point is serious. If one axion or axion-like particle is found, it may not be alone. Nature may contain a hidden sector of very weakly interacting fields, with the original axion as only the first doorway. Discovering one would encourage searches for others. It would suggest that the dark side of particle physics may be rich, not empty. If axions are dark matter, they might reveal new kinds of structure in galaxies as well. Because axions are very light, their quantum wave behaviour can be relevant in ways that differ from heavier particle candidates. Depending on the exact mass, axion or axion-like dark matter could form coherent waves, clumps, streams, or subtle interference patterns. These effects might influence the inner regions of galaxies or produce small variations in the dark matter density near Earth. Some versions could form dense objects, sometimes called axion stars, though whether such objects exist depends on the model. The point is that dark matter might not be a featureless invisible fog. It could have texture, it could have waves, knots, and local variations, all governed by physics we have not yet measured. That would make the Milky Way feel different. At present, we picture ourselves orbiting within a galaxy of stars, gas, dust, and dark matter. If axions are confirmed, the dark matter halo becomes a specific physical environment, not just an inferred mass distribution. Earth would be moving through an axion field. Detectors would be sampling that field. Seasonal changes, daily motion, and galactic structure might all become relevant to how the signal appears. The laboratory would become a kind of local weather station for dark matter, though the weather would be made of a hidden field rather than wind and rain. One could imagine future maps of the axion environment around the solar system, built not from light, but from faint laboratory signals gathered over time. The discovery would also sharpen the relationship between astronomy and laboratory physics. Dark matter began as an astronomical puzzle, seen in galaxies and clusters. The Axion began as a particle physics solution to a strong force puzzle. Experiments now try to connect the two inside shielded rooms on Earth. If an Axion signal is found, it would be a triumph of that connection. The same particle would explain observations made with telescopes and measurements made in particle laboratories. A magnet in a basement and a galaxy millions of light years away would be studying the same hidden substance. That is one of the most satisfying possibilities in science, when different methods, scales and traditions converge on one answer. An Axion would also teach us about naturalness, though that word can be slippery. Physicists often wonder why certain quantities in nature take the values they do, especially when they seem unexpectedly small or delicately balanced. The strong charge and parity mystery is one such problem. The Axion provides a dynamic explanation rather than a coincidence. If it is found, it would encourage the idea that some apparent fine-tuning in physics may be resolved by hidden fields and symmetries. That would not solve every naturalness problem, but it would show that nature sometimes does use this kind of mechanism. It would give physicists reason to keep looking for similar explanations elsewhere. At the same time, the Axion would remind us that explanation can be indirect. Nobody saw dark matter first. They saw galaxies moving strangely. Nobody saw the strong force setting directly. They saw that a neutron property was absent to astonishing precision. Nobody sees the Axion field with the eye. They build a detector and wait for a photon, a shift, or a resonance. Much of modern physics is like this. We do not always encounter reality face to face. We infer it through effects, patterns, absences, and constraints. The Axion, if found, would be a lesson in trusting careful indirect evidence while still demanding direct confirmation. There is a philosophical edge here, but we do not need to become too misty about it. The practical statement is clear. Reality includes things that human senses cannot detect unaided. That has always been true. We cannot see radio waves, neutrinos, ultraviolet light, or magnetic fields directly, yet they are real and measurable. Dark matter may be another step in that lesson. Axions would extend the range of the unseen. They would show that something can be almost completely invisible to light and still dominate the matter budget of galaxies. They would make the familiar world feel less complete, but more interesting. One of the most exciting consequences would be that the strong force mystery and dark matter would no longer be separate entries on a list of unsolved problems. They would become two views of one deeper structure. This is often how physics advances. Electricity and magnetism were once separate phenomena, then became one electromagnetic theory. Space and time became space-time. Particles and fields became different descriptions within quantum field theory. If the Axion is real, a symmetry problem in nuclear physics and a mass problem in cosmology become linked. The universe would be telling us that its hidden connections are more economical than our categories, and yet, even if Axions are discovered, many questions would remain. Does the detected particle truly solve the strong charge and parity problem, or is it an Axion-like cousin? Does it make all of dark matter, or only part of it? How was it produced in the early universe? Did its associated symmetry break before or after inflation? Are there additional related particles? Does the Axion interact with other hidden sectors? Can it help explain any astrophysical anomalies? What does it imply about high-energy physics beyond current experiments? A discovery would not close the book. It would open a thicker one, possibly with smaller print and more appendices, which is how physicists secretly prefer it. The search for Axions therefore reveals something about reality even before discovery. It shows that the universe can be constrained by absence. It shows that invisible matter can be studied through motion. It shows that tiny precision measurements and vast astronomical observations can belong to the same investigation. It shows that modern science is not only a hunt for bright objects, but a discipline of listening carefully to what does not immediately appear. Whether the Axion is found or not, the search teaches us how to ask better questions of the dark. If the Axion is found, the universe becomes more understandable and more mysterious at the same time. More understandable because two great puzzles may share a solution. More mysterious because the solution reveals a hidden field we had not confirmed before. A new layer of matter that has been around us all along. That is often the pattern. Discovery does not shrink the universe. It gives it depth. The map gains detail, and the horizon moves farther away. So what could Axions reveal about reality? They could reveal that the neutron's silence is not accidental. They could reveal that dark matter is a field born from early cosmic history. They could reveal that the visible universe rests inside an invisible structure made of particles lighter and quieter than anything in ordinary experience. They could reveal new symmetries, new fields, and perhaps new sectors of physics. They could show that the laws of nature are tied together across scales so vast that a particle inside the atomic nucleus and a halo around a galaxy are part of one explanation. And that brings the story back to the darkness itself. For centuries, darkness in astronomy mostly meant distance, emptiness, or lack of light. Modern physics has made it something richer. The dark is not necessarily empty. It may be full of structure, particles, fields, and history. If the Axion is real, then the darkness around galaxies is not a blank backdrop. It is an active ingredient of the cosmos, quiet enough to pass through us unnoticed, but strong enough in total to shape the architecture of the universe. The remaining question is simple to ask, though not simple to answer. If the darkness really has a particle, what would it mean for everything we thought was ordinary? If the darkness has a particle, then the night sky is not only a view into distance, it is a view into incompleteness. Every bright star, every pale galaxy, every glowing cloud of gas would be only the visible part of a much larger arrangement, one whose main substance does not shine at all. This is the strange possibility the Axion gives us. It suggests that the missing matter of the cosmos may not be hidden in dead stars, cold planets, or ordinary objects too dim to see, but in a field of extremely light particles passing quietly through space, through galaxies, through Earth, and perhaps through the room around you right now, with no more ceremony than a thought crossing a tired mind. That is a remarkable idea, because darkness usually feels like absence. Turn off a lamp and the room disappears into shadow. Look between the stars and the blackness seems empty. Close your eyes at the end of a long day and the dark becomes a place of rest. But in modern physics, darkness has become less like emptiness and more like a question. The universe is telling us through gravity that something is there. It is not bright, it is not atomic, it is not made of the same familiar material as planets, people, oceans, dust, or the toast crumbs that somehow migrate across a kitchen with no respect for geography. But it has mass, it gathers, it shapes, it holds galaxies together, it bends light, it leaves marks in the oldest radiation we can observe. It is invisible, but it is not irrelevant. The Axion is one of the gentlest ways this darkness might become physical. If dark matter were made of very heavy particles, we might imagine it as a kind of invisible cosmic gravel, individual pieces drifting through galaxies. But Axion dark matter would be different. Because Axions would be so light, and because so many of them could occupy the same state, they may behave more like a broad, coherent field than a swarm of separate little pellets. The Milky Way could be surrounded by and filled with this dark field. The sun would move through it. Earth would move through it. The laboratory, the ocean, the city, the quiet bedroom, all would move through it. And yet nothing would feel different, because the Axion would barely interact with ordinary matter. It would not rustle a curtain, warm a hand, or leave a trace on a mirror. Its presence would be known through gravity, and perhaps through one rare conversion into light inside a detector built with almost unreasonable care. This is one of the most interesting features of the Axion. It could be everywhere and still be almost impossible to notice. That is not how ordinary experience trains us to think. We expect important things to announce themselves. Fire is hot, water is wet. A falling book makes a thump. A cat demanding breakfast can generate a sound far larger than its body should reasonably allow. But the universe does not measure importance by loudness. Gravity is quiet too in everyday life. You do not hear the earth pulling you downward. You do not see gravity as a colour in the air. Yet it shapes every step, every orbit, every falling leaf, every tide. Dark matter may be similar. Its individual interactions may be nearly silent, while its total influence is cosmic. If the Axion is found, the darkness gains identity. It stops being only a placeholder in the equations, only a missing term in the mass budget, only an unknown substance inferred from motion. It becomes something with properties. Scientists could measure its mass, its interaction strength, its abundance, and its behaviour in the galaxy. They could ask whether it truly solves the strong charge and parity problem, or whether it is an Axion-like relative with a different origin. They could study whether it forms all of dark matter or only part of it. They could compare signals from different experiments, from resonant cavities, solar telescopes, light shining through wall searches, atomic sensors, and perhaps instruments not yet invented. The dark would become a laboratory subject. That would be a turning point. For decades, dark matter has been one of the great inferred realities of science. We see its effects, not the thing itself. We watch stars orbit too quickly in the outskirts of galaxies. We see galaxy clusters hold together with more gravity than visible matter can supply. We map the bending of light and find mass where there is not enough glow. We study the cosmic microwave background and find that the early universe needed a dark component to develop into the structure we see today. These are not vague hints. They are strong repeated lines of evidence, yet they do not tell us what dark matter is made of. Discovering an Axion would give the invisible matter a particle nature, or more precisely a field nature expressed through particles. It would turn a gravitational mystery into particle physics. It would also make the strong nuclear force feel different. The Axion did not begin as a dark matter idea. It began as a solution to a problem inside the theory of the strong force, the force that binds quarks into protons and neutrons and helps hold atomic nuclei together. The problem was that the strong force appears not to violate a certain combined symmetry, involving charge and mirror behaviour, even though the theory allows it. The neutron should have shown a tiny internal electric imbalance if that violation were present, but experiments have found no such effect. The Axion explains this by adding a field that naturally relaxes the strong force into the balanced state we observe. If the Axion is real, then the neutron was not merely quiet by accident. Its silence was caused by a hidden mechanism. That is a beautiful kind of scientific connection, although we should use the word beautiful carefully, because nature is not obliged to be beautiful in the way we prefer. Still, there is something satisfying about one idea solving two problems. The same particle that explains why the neutron does not show a forbidden-looking internal imbalance could also explain why galaxies have more mass than they visibly contain. The smallest and largest scales would be joined. A measurement of a neutron in a laboratory and the rotation of stars around a galaxy would become clues from the same underlying story. That is the kind of unity physicists often hope for, not because the universe must be simple, but because sometimes separate mysteries are separate only from our point of view. If the darkness has a particle, then ordinary matter becomes less central in the cosmic story. This does not make ordinary matter unimportant. It makes stars, planets, chemistry, bodies, rain, trees, sleep, and every known living thing. Ordinary matter is the part of the universe that became complicated enough to wonder about the rest. That is no small achievement. But in terms of total matter, it is not the majority. The familiar material of experience may be only the bright interactive fraction. Dark matter may be the larger, quieter foundation. If axions make up that foundation, then most matter in the universe does not participate in the kinds of interactions that create colour, touch, and chemistry. It is matter without surfaces, matter without light, matter that shapes structure while remaining almost completely outside the habits of ordinary life. There is a humbling lesson in this. Human beings are built from atoms, and atoms are naturally persuasive. They fill our senses with evidence. They make the floor firm, the air breathable, the kettle hot, and the sky blue. It is easy to mistake atomic matter for matter itself, as if the stuff we're made from must be the standard. But cosmology says otherwise. The universe is not arranged around what is convenient for human intuition. It contains neutrinos, black holes, quantum fields, curved space-time, and perhaps axions. It contains things that pass through us, things that bend light, things that exist only briefly, and things that may fill galaxies without shining. The ordinary world is real, but it is not complete. An Axion discovery would also give us a new relic from the early universe. Relics are one of the ways cosmologists read the past. The cosmic microwave background is relic light from when the universe first became transparent. The abundance of light elements is a relic of early nuclear reactions. The large-scale web of galaxies is a relic of small density variations amplified by gravity. Axion dark matter would be a relic of a field that began moving when the universe cooled and the strong force took on its modern behaviour. That means the dark matter around us today could be a preserved motion from the infancy of the cosmos. Every galaxy would carry, in its invisible halo, an echo of a field settling into place billions of years ago. This would make the early universe feel less remote. It is tempting to think of the beginning as something sealed away behind time, an event so far back that it belongs to another kind of reality. But the early universe is still here in its consequences. It is in the hydrogen in water, it is in the helium in stars, it is in the background radiation passing through space. It is in the arrangement of galaxies. If axions are dark matter, it is also in the invisible mass flowing through the Milky Way. The past did not vanish. It changed form. It became the conditions of the present. If the axion remains undiscovered, the story is still valuable. Science often advances by learning which beautiful ideas nature refuses to use. A failed search, if done carefully, is not a waste. It closes doors, it sharpens questions, it forces theories to become more precise. It tells us that a particle cannot exist with certain properties, or cannot account for all dark matter in certain ways. The darkness becomes more constrained. The remaining possibilities become fewer, clearer, and sometimes stranger. There is dignity in that kind of progress. It is not the dramatic joy of discovery, but it is the patient discipline that makes discovery trustworthy when it finally comes. Still, one can understand why the axion has held attention for so long. It is not merely a guess, it is a well-motivated possibility. It arises from a real theoretical puzzle. It naturally has the faint, stable character dark matter needs. It can be searched for with actual experiments. It appears in broader theoretical landscapes as well, where axion-like particles may be common, and it carries a certain intellectual economy. It says that the universe may have solved a nuclear symmetry problem in such a way that it also produced the dark matter. That is not proof. But it is enough to keep magnets cold, cavities tuned, telescopes aligned with the sun, and physicists listening. The search itself is almost a portrait of modern physics. It is not one single heroic machine. It is a community of different instruments asking related questions. Some listen for microwave photons produced when galactic axions pass through a magnetic field. Some watch the sun for axions that might stream from its core. Some send light toward a wall and wait to see whether hidden particles carry the signal through. Some use atoms, nuclei, or quantum sensors as delicate monitors of a passing field. Each method covers a different region of possibility. Together they form a slow, careful survey of the invisible. The darkness is being searched not with one lantern, but with many kinds of quiet attention. If an Axion signal appears, it will have to survive doubt. That is important. A faint excess in a detector is not enough by itself. It must be checked against noise, interference, equipment effects, background events, and all the ordinary ways nature and machinery can imitate something interesting. It must return. It must make sense. Ideally, it must be confirmed by another experiment using a different method. Only then does a signal become a discovery. This caution is not pessimism. It is the reason science works. When the claim is that we have found the particle that may make up the invisible matter of the universe, the evidence has to be stronger than excitement. And if it happens, the consequences would unfold over years. First would come confirmation, then measurement, then comparison with cosmology. Does the amount match the dark matter density inferred from the universe? Does the signal vary as expected with Earth's motion through the galaxy? Does it agree with limits from stars and laboratory searches? Does it fit the original Axion model, or a broader Axion-like particle? Could there be more than one? What does it imply about the symmetry-breaking scale in the early universe? What does it tell us about inflation? A discovery would answer a question, then immediately give birth to many smaller, sharper questions, because that is how knowledge behaves when it is healthy. The emotional temptation is to imagine the Axion as the final missing piece. But physics rarely ends so neatly. If the Axion is found, it will not make the universe simple, it will make the universe more specific. We would still need to understand gravity at the quantum level. We would still need to understand the full origin of matter over antimatter. We would still need to know why particle masses and families have their particular patterns. We would still need to explore whether other hidden fields exist. The Axion would not close mystery, it would move it. It would turn one large dark outline into a detailed object, and then we would notice the shadows behind it. That is not disappointing. It is one of the most comforting things about science. The aim is not to run out of questions. The aim is to replace vague questions with better ones. What is dark matter is a great question, but it is broad. If the answer is axions, we can ask what kind of axion, how heavy, how strongly interacting, how produced, how distributed, how connected to deeper symmetries. The unknown becomes more navigable, the map gains contour, the darkness does not disappear all at once, it becomes a landscape. There is also a personal scale to this cosmic thought. If axions are dark matter, then the dark matter is not simply out between galaxies, it is local. It is passing through Earth, it is passing through us, not in a mystical way, not in a way that affects your thoughts, dreams, or mood. There is no reason to imagine axions as a hidden spiritual current or a secret biological influence. They would interact far too weakly for that. But physically, quietly, they would be present. The human body would be immersed in a dark matter halo, just as it is immersed in gravity and radiation, and fields too subtle to notice unaided. We would be living inside a hidden layer of the galaxy. That thought can settle gently rather than dramatically. Nothing about the room changes if it is true. The lamp still glows, the bed still supports you. The ordinary world remains ordinary, but beneath the ordinary there is depth. A cup on a table is made of atoms, held together by electromagnetic forces, resting in Earth's gravity, moving around the Sun, orbiting the centre of the Milky Way, and possibly passing through an Axion field that began as a solution to a strong force puzzle in the early universe. Everyday things are not less familiar because of this, they are more connected. Perhaps that is what the Axion story gives us, even before discovery. It teaches us that reality may be connected in ways that do not announce themselves. A missing neutron effect, a galaxy rotation curve, a cool detector, and the first moments after the Big Bang may all belong to one chain of reasoning. It teaches us that quietness can be evidence, that invisibility can have weight, and that a particle almost impossible to detect can still be worth decades of careful attention. It teaches us that the dark is not simply a blank place where knowledge stops. Sometimes it is where the next layer begins. So if the darkness has a particle, the universe becomes both stranger and more coherent. Stranger because most matter may be something we have never touched, seen, or directly detected. More coherent because that same hidden substance may arise from a mechanism that explains a deep symmetry puzzle. The stars would still shine, but they would shine inside a larger dark structure. Galaxies would still turn, but their turning would be guided by an invisible field. The neutron would still seem balanced, but its balance would have a cause. The early universe would still be distant in time, but its field motions would remain around us as dark matter. And here, at the end of this long quiet journey through the Axion, we can return to the simple feeling that began it. The universe is not finished with us. It has not shown all of its contents. It has allowed us to see enough to become curious, but not enough to become complacent. We have learned that matter can be stranger than atoms, that darkness can be heavier than light, and that silence inside a neutron may point toward the mass of a galaxy. The Axion may be real, or nature may have chosen another answer, but the search itself is already a reminder that science is a patient conversation with the unseen. And now, wherever you're listening from, whatever time it is in your corner of the world, perhaps the room has grown a little quieter, perhaps the day has loosened its grip, perhaps the idea of dark matter passing silently through the galaxy feels less like something frightening and more like something spacious, a reminder that reality is larger than what presses immediately against the senses. If you found this journey calming, or if the thought of hidden particles and gentle cosmic mysteries helped you settle into the evening, I would be very grateful if you liked the video, subscribed, and shared this sleepy space with someone else who enjoys science at a slower pace. The darkness above us may not be empty. It may be full of particles, fields, and ancient history. But for now, in this small moment of ordinary time, there is only the quiet, the breath, and the soft edge of sleep. Rest well, fellow traveller, wherever you are and whatever unseen universe is passing gently through the night.